intensive course lectures. Today we're going to be speaking about intervention trials. I will start with the most important one, randomized clinical trials. And it's a long lecture, a lot of material, good material. I think you're going to follow this very easily. I do believe so. I have more examples than I had yesterday, because yesterday was too statistical, and to put an example in everything would make you even more complicated, okay? Whereas here is the application. So there's application, you need to show how is it apply, and that's what I'm showing. I show some good examples here, what are we talking about. But we'll be talking about the randomized clinical trials, which are the top of the form in terms of intervention trials. What are the intervention trials? That you do an experiment, but you intervene, and that's why it's intervention trials. So if I could be, break down all the classifications of intervention trials into randomized and non-randomized. That'll be an easy way to do it. There's more to it, and I hope I'll get some of that nuance by understanding better what the randomized clinical trial is, and then moving forward with the other example. If we have an opportunity at the end of the morning today, I will show you a presentation, it's not a lecture, about how we designed something very unique and different. That's not your traditional randomized trial, and it's an application that was well received, and it was done here in Brazil. So I'll have an opportunity, hopefully, to show it to you. So without further delay, let's get started. So intervention design, that's what we're going to talk about. We're going to talk about strengths and limitations, but more important, we're going to guide you step by step how to actually implement it, okay? We're going to be talking about how do I randomize, how do I select samples, what kind of power should I have, what kind of statistical testing I'm supposed to do, and then the little bit of variation, the designs that can be done with it. So you all know now that we have a group of studies called observational studies, because they are not intervention studies, and therefore we just observe natural phenomena. People taking up smoking, it's their decision. The people, we just observe it. Whereas here, if I'm going to do an experiment and it's about smoking, I will force or get people to smoke, which is different. So I control the intervention, and therefore I am the researcher. I'm doing what we call an intervention trial. So the study designs can be further classified, like I told you, into randomized, non-randomized experiments and observational designs. In the non-randomized experiments, which I hope I'll have a small chance to do it by the end of the day, and I'll bring an example. We have many possible combinations of studies, but they try to mimic, again, a randomized study without randomization. So let's see this tree, a decision tree, and whether we have what it takes to do a study. And you can see on the left hand, on my left hand, which is your, if you're there looking at me, it'll be your right hand. You're going to see, yes, I can assign exposure. I can assign an intervention. Exposure here is corollary for intervention or treatment. I can assign the treatment. I can assign the intervention. Okay, that's a yes. Or I cannot assign, that's a no. Therefore, you have an observational design. I told you, cross-sectional, we went over this, surveys, case control, which is a little bit better, cohort, which is the best of all observational design, and sometimes, and most often, is the only option we have, because intervention trials are not always ready for you or me or the patients because of ethical issues. But if you have an opportunity, you can assign the treatment, you can assign the intervention. You want to go for an intervention trial. Well, intervention trials, you ask the next question, can I randomize? Yes, I can assign exposure, that's an intervention trial. Can I randomize? Yes or no? If I can randomize people into intervention and no intervention, then I have something else. I have the randomized trials, of which the clinical trial is the golden standard, the randomized clinical trial. I'll have some word about it at some point here, maybe right now, but let's finish just going through the three. So once you say, yes, I can randomize, then I have an experimental study. I have an experiment, okay? I am Dr., crazy. I can throw the intervention, a person to intervention group, another person go to another group that there's no intervention. I control. I'm the guide of that destiny, meaning assignment of individuals to treatment and non-treatment, intervention, non-intervention. And in there are many possibilities. You have randomized control trial, which is the classical trial, cluster randomized trial, stepwise design. Hopefully I'll have a chance to talk about that. Adaptive design, hybrid design. To be truth to you, it will take a whole week to fully cover adaptive design and hybrid design. Okay, so I'm not even going to touch it. I gave a seminar here about 2 years ago that I went over a little bit for an hour on these guys, but it's not sufficient. You need a whole week studying it. So you have experiments. Now, what I mean to the word randomized clinical trial, when you say randomized clinical trial, the origin of that terminology was meant for clinical population, means patient population. And it came out historically from the trials to test drugs, to test medication, okay? So in that scenario, you do have patients only as your subject. Therefore, you have a randomized clinical trial. Well, even in our age now, or many people are using randomized clinical trial to mean randomized intervention trials. So don't get confused. It's the wrong terminology, just like calling a risk, oh, that's a cumulative incidence rate. Oh, prevalence rate. That's not a rate. Prevalence is a proportion and risk is a proportion, not a rate. But here's the same situation. Randomized clinical trial, they throw that word for everything, any randomized intervention trial. But it's actually the origin of the term, and the right way to use the term is for randomized clinical trial, patient population. Just a little point. And the non-experimental side, you have so many. I just gave you a few examples. I have an example here for you of a regression discontinuity design. Hopefully, I'll be able to get to it. Actually, it's not. I take it back. It's a difference in difference design, very much used in economics. But I designed a study for it to evaluate the pre-Obamacare health system in U.S. It was called the Massachusetts experiment by Governor Mitt Romney, who is now for the past 20 years a senator in U.S. So I designed a study which used what I call difference in difference type of design, which is a non-randomized, it's a quasi-experiment because you control the intervention, but you don't control the randomization. You don't have randomization. So we'll talk about that later. Once you have your experimentation, you're going to have levels of randomization, okay? And there are many levels. We're going to go over a few. I'll try to skip some because I have so much material, good material to cover with good examples that I don't want to take forever going over that, okay? So the level of randomization can be at the individual level, okay? And you can have RCTs, randomized clinical trials, stepwise design, and some other variation too. It can be factorial, it can be not factorial, it can be different ways. I'm give you a few examples at the very end of this lecture specifically. And you have multiple split plot design, very complicated, but very useful. And then you have the cluster randomized designs, which can also be implemented as a stepwise design or late start design. That's another terminology used. So I'm throwing all those words so you can see it. I cannot cover all of that in this intensive course, but each of those designs requires a whole course on it. Swear to God, because of the intricacies of the analytical steps that you take it. And the reason you do some of those things is pragmatism. Sometimes stepwise design, I hope I'll get to it, allows you to get to larger population to be acceptable, politically correct, so to speak, and ethically more amenable to adaptation, whereas the other design may be too inflexible. So bear with me, there's variation of the theme called randomized intervention trials, and which randomized clinical trial is the golden standard and has been used historically for clinical population, but now they throw the word for anything. What they actually mean is randomized intervention trials. So we're dealing now with randomized clinical trial. Okay. Now it's going to go like that now. One of those delay things. I don't like that. I don't know how it started, Fred, but
Excuse me, what's the problem?
No, it's like you press the button and the slide comes, the information comes little by little.
Slow motion.
Slow motion. I don't like that. An intervention study is a comparative study of two things, right? I'm comparing intervention in one group versus intervention in another group. There's nothing to it, okay? The participants exposed to the intervention, and ideally is that intervention allocation is determined randomly, meaning I don't say you take it, you take it. I'm just saying randomly, the random number told me you are supposed to take this intervention, you are not. Yeah, we know that, but let's mention, because I think most people know about it. So one intervention is versus another intervention, but usually in clinical trials with patient population, chemicals or drugs or any type of medicine, you like to see a placebo group. A placebo group is a group that takes a medication or a treatment that in every shape and form, it looks exactly like the treatment, and they don't know. And that's another word. It's blind. The patients are blind to what they're taking. They think they're taking a medication, but they may be not. Okay, so that's called placebo, group. The placebo group is having a medication that's like a fake, like a pill of sugar. Okay, and therefore it avoids the important bias, which affects the whole design. It's an information bias, actually. It's not a selection bias. It's not the manner in which I select people into the group. That's randomized here. Everything's randomized. There's no selection bias. At least if the large numbers are applied, very seldom you're going to see a bias due to the selection because you're randomizing. And I'll explain that a little bit more later. But the placebo avoids the patient being more willing or less willing to be one way or the other because they think they're being treated the right way. So everybody's being fooled here. I'm fooling everybody. I'm just saying, hey, you're having great treatment when you're having a pill of sugar. That's called placebo. We'll talk about that later. So you got your intervention design. In this case, I'm talking about randomized clinical trials. You randomly assign people. Don't forget, you always have eligibility, ineligibility. And you use that to make your study more efficient, to prevent bias from creeping in later on, okay? And to avoid ethical problem. And then you have the issue of participation or participation. I'm not gonna deal with that, but there's a whole lecture about the ethicality of creating incentive for people to be in the study. Incentive could be money, could be treatment that goes free, a lot of things that goes in, okay? But that helps participation. I usually use some form of incentive. I don't see any ethical problem in it. I think it would bias the studies if I do one thing in one group and not doing the other. Don't do it. Do it everybody equally to create an incentive for their participation. And therefore, you don't want to lose people. Remember, a clinical trial is very similar in terms of orientation to a cohort study. And in a cohort study, you want to select exposed and exposed group without bias. Here, I want to make sure that people select into the group without bias. And that's why I randomize. It's perfect, right? But if I have a lot of no participation, remember the randomization, people sometimes forget and they do randomization a little bit too early when they find the eligible people. And then later on, they don't participate. That's why I put the order here. Can you see that it's pink as opposed to yellow, gray? That's a mistake. Many people, I've seen a few studies came to me, people randomized after people have decided to participate or not participate. Okay. You're doing some good, definitely, but it's not good enough because I don't know if the people who don't participate are too different than the people who are in. So you bias in study, you're creating selection bias, even though you're doing randomization. The randomization people, the only thing you do with randomization, try to prevent bias to creep in, like selecting people based on something. No, you randomize, meaning you take a random number, give people in a select population, give them a fake number, and then you randomly sample from that fake number draw. Once you have that person, they are in the study for treatment or they're in the study for non-treatment. So in doing that, you prevent this selection bias and confounding. We're going to deal with that later on when you talk about the analysis. But if you do the randomization before you are certain the people are going to participate in the study, you incur the risk of losing some people after you randomize it. And therefore, you bring the bias back in. So once you randomize them, you have exposed to the treatment, unexposed to the treatment, exposed to intervention, unexposed to intervention. I may not have a chance to talk about that. I'm going to talk right now. Intervention trials. So how many trials do you remember, or do you hear, or do you know? I'm focused today on clinical trials, meaning focus on the traditional randomized clinical trials, thinking about a clinical population of patients. But intervention trials more than that. And let's throw some field numbers. Field trials. What do you mean by field trials? Well, let's say I'm in 1960. I'm still debating whether fluoridation of the water makes good for the population, brings any benefit or not, or maybe bring more harm than benefit. So I do a field trial. What do I mean a field trial? Well, I create communities across a region in which some of the small towns and cities have fluoridized water. The others don't. And then I follow them over time, whole community, the entire community, and do a survey, baseline, survey in the middle, survey in the end. I'm doing a field trial. I randomize the community into treatment with fluor in the water and non-treatment with fluor in the water. I randomize it. So it's an intervention field trial. You got it? Another intervention trial, that's not, we don't call field, because actually the unit of selection is the individual, is vaccine trials. You know, large population vaccine trials. We bring a lot of people, not, well, we're going to get into that, phase 1, phase 2, but we're talking about final phase effectiveness trial. You deal with the general population, so you sample people randomly from different places, different cities. It's an intervention trial. That's not a clinical trial. Just be aware that the most important thing is the randomization, okay? And for patient population, placebo, and the other one is blindness. We're going to talk about those issues. Reasons for conducting: uncertainty exists about the effect of alternative treatment. So you need to have a hunch, or somebody should have placed a hypothesis to be tested. You want to test whether new intervention is going to do better for the improvement of the health of this person or this type of patient than their standard treatment. That's a fair question. Or you want to say this is completely new treatment for a disease that never had a treatment, therefore you do a placebo. Or you can have a situation you have new treatment, existing treatment, and a placebo. You can have 3 groups, okay? But, you know, you need to compare treatment to something, and that something is usually standard treatment or a placebo, or both. Exposure of interest is modifiable, and persons participating in style willing to relinquish control of the exposure. Okay? That's another reason why we do a trial. Okay, an intervention trial. Would you do an intervention trial on something that you can prove but you cannot change? Like it's hard to. I should have brought an example, but I do an intervention trial like we did for tobacco, a large population in U.S. and people quit smoking better if I create some kind of incentive, okay? Because I knew I could legally and officially get rid of smoking, technically. I never, in practice, won't happen, but it's feasible. But if I'm trying to change something that's unchangeable, I can prove mathematically, scientifically, there is a trial in effect, but I cannot implement it. So there's no point. You only do things that you actually have a way to change it. Outcome of interest is reasonably common, or the potential effect of treatment on rare outcomes of sufficient importance to justify a large study. I think this is speak by itself, right? The outcome of interest is common. Potential effect of treatment on a rare outcome is sufficient importance to justify a large study. And that's so much a decision for those who are going to fund that study. It's government or a private organization who's funding trials, who's funding research. They look into that kind of a big decision-making thing. There's also something called exploratory preclinical trial designed to answer specific and usually very narrow scientific question, toxicity. And we're going to talk about that, phase 1, phase 2, phase 3. So the phase 1s are more like exploratory trials. Here we go. I told you, I anticipated myself. It's been a while since I gave this lecture. So phase 1 trials are actually toxicity studies. They're preclinical. We're not really understanding how the drug or the treatment works. It's just trying to understand, is that toxic? Because otherwise it would be unethical to get people involved in large trials and doing stuff like that. And they usually involve trials that may involve animal in very selected group of people, mature people, totally aware of the risks and have a lot of incentive to take it. But it's questionable if you use humans to do a toxicity, but it's done. Phase 2 trials is small-scale studies designed to evaluate dose-response relationship and the adverse effect rate of the drug. Not the toxicity, but it's adverse effect, a combination of what the toxicity could be, but sometimes unexpected things. You prove the drug in phase 1 is not toxic. Theoretically, it's not toxic. But in life, in practice, once you deliver, things may happen. Interactions that you didn't see it. There was not enough time in the toxicity study for things to take effect. People are still questioning whether these new vaccines like the Moderna and Pfizer, in the long run, may cause harm. You know, I'm fully aware. I took 5 of those vaccines because I reviewed very carefully the phase 1 and phase 2 trials of these vaccines. And I know the people, and I know the research around coronavirus very well. And it's over 50 years we've been studying coronavirus. We knew that will be the 3rd or 4th or 5th. We're expecting another one very soon. Yes, there's those conspiracy theories. People are just ignorant and press like to make a lot of noise about it. We know about coronavirus forever. There's books written, there's papers written, and there are a lot of memos we write to each other, say, when is going to be the next one? It's not because we're creating the epidemic. It's because we've been studying since the mid-60s. I think it was 62 when you start studying coronavirus, a potential virus to jump to humans and cause mass epidemic. At any rate, so trials on small scale, that's a phase 2, and you're really interested to prove the concept that that intervention is actually moving the needle in the right direction, is making the outcome of your interest improve in the right direction. You still don't have power. You don't need to have power at that stage. You need just to prove you already done the toxicity. You prove that. Usually, this is very common to drugs. Okay, drug trial. Come on. And then you have the clinical phase, okay, designed to guide practical decision-making between alternative treatment. That's what the main purpose of the randomized clinical trial. Really, the randomized clinical trial starts here, but you can apply the principles also to the phase 2 studies, okay? But it's really, that's what I'm talking about, the clinical phase. Phase 3 is, you've gone through the toxicity, you've gone to the phase 2, and then you are in the clinical phase. That's the clinical phase. We also call phase 3. There are large-scale studies conducted to evaluate the efficacy of the drug. And again, a word of caution to all of you: efficacy, effectiveness. Efficacy is the measure you extract from a traditional randomized clinical trial, blind, double-blind, placebo control, and randomized clinical trial. So what you extract from this is an efficacy measure. It shows how efficacious the drug is in changing the outcome. Let's say your outcome is A1C. It shows how effective that drug is in lowering your A1C from average of above 7, let's say 7 to 10, median of 8.5 to below 5. Okay? Or from 8.5 to 7 or to 6, some improvement. So that's a efficacy measure. Once I reduce that, that's the effect size. That effect size becomes an efficacy measure, meaning I am doing a randomized clinical trial, double-blind, placebo, and controlled trial. And therefore, I have a measure of efficacy. Why? Because it is a totally controlled environment. Once you do not have that anymore, I'm doing a large effectiveness trial, which I cannot call a randomized clinical trial. Even though I may do a cluster randomized trial. We'll get to that later on, but I still don't control as much as I used to control. That is an effectiveness. Why? Because now I don't have a control environment. I don't have a control time. Because in a clinical trial, say my trial will go on for 6 months, for 1 year, or for 2 years. I have real life. So, example, this is a true story. I always say it's old now. People make fun. Efficacy trials for Viagra. A phase 1, extremely, extremely safe. Phase 2, very powerful to change the direction. Immediately went to phase 3 clinical trials. Powerful, very powerful. Yes, you have an erection like you never had it before. It happened that this is an efficacy measure. Once it came worldwide spread, lots of death, lots, small proportionally. We talk about 1 in 10,000, but lots of death. If you think about all the men in America taking Viagra, it was a phenomenon in the 80s and 90s. Everybody started taking that thing, swear to God. So all of a sudden they have clusters of death, and people are trying to investigate. CDC investigated a famous case. It was a prostitution house in somewhere in Los Angeles, and a group of 50 old men, very old men, full of Viagra, went there, was prostitute, and 3 of them died in one event. Okay, because there's too much sex, too much drug. So that's an effectiveness issue. You see that? The efficacy trial, well controlled, 1 year, nobody had complications. Take as prescribed. You take 1 pill. The guys are going crazy. They'll take 1, 2, 3 pills, priapism, uncontrollable, and death. So that's an effectiveness. I'm making the analysis so people understand. They are using this word. All of you are using this word interchangeably. It's wrong. Efficacy is coming out of a randomized clinical placebo-controlled blind, double-blind trial. That's a measure that's well controlled. Everything is controlled. The medication is done, is given to you right on time. You accept the medication. There's no complication. But in the real world, you're talking about effectiveness. So every time you do a trial involving lots of people outside the realm of clinical controlled trial, that's an effectiveness measure. Luiz has a question.
Just an observation. In the perfect control clinical trial, I thought there was another characteristic, which is an intention to treat analysis.
We're going to see that. I'm just doing the overview. We're going to go over everything. We're going to go to analysis. There's a whole lecture on analysis, but also this one. This is a long lecture, folks. Holding it. You're going to like it. There's a lot of good tables, good numbers. You will remember what you learned from the cohort study. You remember what you learned from Poisson and for binomial distribution. Okay? But I think I made the point case. And there's something else we call phase 4. Focus on long-term assessment and follow-up of the new drug. That is trying to get into effectiveness. Okay, folks? Phase 3 is really efficacy measure. And here we're dealing with maybe effectiveness. If it's still well controlled, I personally don't call effectiveness. I only call effectiveness if I have a natural experiment or quasi, pragmatic trials, a large population, real world population, real life. Oh, this mammography was perfect. Have you seen the mammography I used to work when I was in Pernambuco 40 years ago as a doctor? You trust that mammography? You see what I'm talking about? So you're using stuff in real life that's not like you have in a study. And a study like that, well paid, lots of money, everybody's instructed, it's educated how to implement the study. The patients are blinded to the treatment. The doctors treating the patient are blinded, it's called double-blinded. The scientists handling the statistics are blinded. Okay, everything is well controlled. It's like a perfect environment. Okay, that's efficacy. Phase 4 is trying to get to effectiveness. Focus on long-term assessment and follow up the new drug in the target population via post-market surveillance. It should be perfect, natural experiment here. We'll talk about that later. And therefore, the phase 4 can get you an effectiveness measure. That's a real life measure. Okay, I don't have time, but usually there's something. I'm going to waste time if I try to get to it. But there's a whole area here about how a new intervention gets to people. Okay, and it takes time, but more importantly, it takes adaptation, and there's a filtering. So original ideas are filtered in such a way that if you have a perfect drug that has an effectiveness of 80% reduction on something, in real life, it may be 10% because of patient compliance. People who prescribe don't know how to prescribe. The patient don't have the money to buy the total treatment and a lot of things. So your effectiveness, your efficacy of 80% become an effectiveness of 10%. That's what I'm trying to talk about. Use inclusion-exclusion criteria to improve efficiency, ethical issues to be addressed, and more importantly, the subject matter of your interest. You're trying to avoid bias to come in creeping in pregnant women for ethical reasons, but also hormonal changes may affect, depends what you're trying to study. So you're trying to eliminate things, and you also can use inclusion criteria to make sure that people are more comparable, even though you're going to randomize, supposed to be comparable. But if you bring people from different age groups by chance, if your randomization is small numbers, you may end up with a little bit unbalanced in age. So you want age to be balanced in gender. Why age and gender need to be balanced always in any study, ideal study? Because as you get older, you get sick. As you get older, you're more likely to die. I'm closer to die than any of you who are in your 20s, 30s, and 40s and 50s. You know, so that's a fact of life. And gender, because of hormone, because women and men are extremely different. That's X and Y and XX. And that determines a lot of our hormone early in life at age 1, 2, 3. The kids are already differentiated. Yes, I know there's something called gender now, but gender always existed, okay? And it's a way we classify. And I know there's some social, ecological issues related to it, but biological, we're extremely different. And we know people do clinical trial over and over like we did, know that very well. So we need to find a way to get gender and age very clear about that. And also you want to exclude some diseases or include some because that's what you're interested in. So inclusion and exclusion criteria may be a way for you to increase efficiency. The aim of the study can be improved as well as avoiding ethical issues. Eligible study participants be fully informed of the nature of informed consent. Not going to get too much on this ethicality, except to read through the list. Participation research, that's what the consent should say. Proceeding protocols involved in research should be clearly explained and the consent to the people who are going to be the subject in that study. All possible risks and side effects should be clearly elaborated in the document. Alternative procedures of possible advantage to study participant needs to be clearly defined. You need to say there's an advantage for you. If you participate, you may gain knowledge about this and that. You may gain an exam that will be completely free for you and so on and so forth. Okay. Degrees of confidentiality, you need to tell people how you're going to keep their information totally confidential and demonstrate to them that you can do that. Compensation available in the event of injury or harm. You need to be clear that this compensation, this is a pickle in many government because the COVID was a pandemic and people are trying to throw that under the bus, and they did in many places, which is wrong. It's wrong, and many of scientists like me and many others wrote a manifest on this. It should not have been relinquished that, but it was relinquished on those vaccine trials for COVID. Compensation available in the event of injury, meaning the companies are basically saying, I have no harm. If something goes wrong, it's not my fault, and you have to accept government. So almost every government balked and complained, but most of them accepted wrongly. The real scientists who deal with that say this is wrong. Who to contact with questions about the study? It's a good long list, but it's good that you see just a list. Voluntary nature of participation, their right to withdraw without penalty. That's a freedom they have to have. And that's so much for the ethical consideration. I'm not going to get each one of them. You could see example. I'm not going to go to that. Okay. So let's go to the randomization process. You need to randomize people into groups so that they are randomly or by statistical of nature, equally, except for the treatment I'm giving them. That's what the aim of randomization. We want equal distribution of measure characteristics in trial arms. By the way, the word trial arms is saying if you're in a treated group, you're in a treatment arm. If you're untreated group, you're untreated arm of the trial. And sometimes you have 5 arms of the trial. Treated with drug A, treated with drug B, treated with standard drug and placebo 4. You can do things like that too, okay? Randomization increases the likelihood that unmeasured variables, that's the confounding folks, are equally distributed between the 2 arms. Increase the likelihood, doesn't guarantee. That's why sometime we're going to talk about block permutation, block randomization, and stratification within the randomization. Randomization in assigning the intervention promotes avoidance of bias. I have to go quick because I have a lot of material to show. Okay, we're already 25 minutes into it. The randomization scheme assignment is abnormal in advance. People don't know in advance. I don't want people to know because they can't play with that. The scientists in the field, I've had example of scientists in the field playing with that. Systematic sample is known in advance, so you don't use systematic sample. If you're familiar with simple random samples, systematic random sample, stratified random sample, cluster random sample, and complex random sampling. I need to go back to basic statistics to learn how that. But the systematic sample, usually you take a random number, and from that point on, you allocate systematically. Every fourth person, every 10th person, whatever. Okay, that's a systematic sample. That one you can play with that. People in the clinics and stuff figure out and stuff. You know, we don't want people to know. We want them blind, right? So the randomization needs to be a normal in advance to most people. Ideally, the schema is a normal, and more important, the individual randomization applied to individuals randomized, not the groups actually receiving treatment or placebo. Well, that's a good point, because I'm focusing now on traditional randomized clinical trials, but then there's something else later on. I hope I have a chance to show to you. It's called cluster clinical trials or cluster intervention trials, in which the unit of randomization is the cluster. You got it? Let's say I have 500 clinics. I randomly sample the clinics, and then I take a random sample of people in the clinic or patients in the clinic, or I take a census, everybody in the clinic. You with me? So the unit of randomization is the clinic, not the patient, right? That creates something else called two levels of variance. I have variance coming from the individual, difference between them across individuals, and I have variance coming from difference between clinics. And people in the same clinic tend to look alike, right? Kind of, because they share the same environment. They are kind of mini cohort. So cluster randomization is not the focus of this lecture specifically. Later on, I'll talk about that. So the individuals are randomized, not the groups. Therefore, analysis is always by intention to treat. We're going to see that later on, again and again. Okay? Intention to treat. No exclusion after randomization are allowed. And that's why people make sure you randomize after your participants already say, we all in. Okay? Don't do that before participants, because you're going to be in trouble. Or try to exclude people afterward. So the randomization, the simple form is a simple random allocation. Study participants are assigned to treatment based on the next number in a random sequence. Even number of participants are assigned treatment, and odd number of participants are assigned to usual care or placebo groups. Very simple, right? And it's totally random. And that's still the best form, because it's simple, everybody understands it, and you don't have problem with that. But there's variation of the thing. We need to go quick on this, folks. I want you to read it, because this is basically breaking down this thing over here and showing an example at the end up. Okay? That's habitual and treatment, the new treatment, and male, female. Okay? But you actually randomize on H&T, not on in male, female. Later on, I'll talk about group randomization or block randomization. You know, you can see how we do that. For small studies, method may result in fairly large difference in group size. I mentioned to you, randomization doesn't guarantee perfect things, okay? So if you have large randomized clinical trials, simple random allocation is the best. But if you don't have enough money, if you don't need a lot of people, because what you're trying to prove, a power calculation, we're going to get to that in this lecture. We're going to see how, I'm going to go 2 examples to you, how to actually do a power calculation, show the formula, very simple formula, and how in real example, real life example from clinical trial. Okay, but if your study is small, you simple random allocation may not do good to you. So you want a permuted block randomization. Okay, group of participants assemble. Half of the participants in each block assigned to treatment, the other half to the usual care or placebo, with order of assignment within block being determined by chance. So you use a random number to determine who gets what, but it's within a block. You separate people into male, female. Okay, if you want to guarantee that male, female are there, you do block by based on gender. Okay, or something like that. Read it again. I put everything for you. You need to go quick, because this is 89 slides. And I want to show you the beautiful of that, which is non-inferiority trials and superiority trials. You need to understand the difference between these two, but that's critical for. So to get there, I need to move quickly here. I want you to read. It's your lecture. You're going to have the lecture later on. I give it to Fred, and he'll send it to you. So this is an example of permutation, okay? You can do random blocks of 2, random blocks of 4, random blocks of 6 usually. So within the block, you randomize. I have only 2 people to randomize, so one is going to get H, the other one is going to get T. But it's within the block. So each block of 2 it's, you know, and the blocks is based on something I'm interested in. Okay. So we're going to go quickly on that. Read it. There's something else called stratification. I can stratify, which is different than block. The smaller the sample size, the more advisable stratification. Same idea here. Age, gender, race, you stratify on these things and randomize within the strata. It looks like a block, but not. The block, I randomize the block, and then within I randomize, you know. Don't confuse that with cluster randomized design, which is something else. Here, the individuals are in blocks or strata, okay? Just read it. This is an example of randomization within a strata. I have the participants. Now I'm going to randomize, but I'm not going to randomize everybody who are participants, not all participants. I'm going to randomize men within men, women within women, into treatment or treatment. And therefore, I guarantee that all the women, it was going to be equally divided. I would have 50% of women to treat, 50% not. But if I had randomized participants, I may end up with 50-50 men, women, but not all women. Though, let's say I have 100 people, for example, and I randomized 100 people into treatment, non-treatment. I got 50 treatment, 50 non-treatment. I may get 70 men in a treatment with 30 women. And here I may get 70 women in a non-treatment and 30 men. You see what I'm talking about? And if gender matters, the sex of that person, because hormone and everything matters big time, then I need to stratify before I do my randomization. So I guarantee that in 100 people, I will have 25 women treated, 25 women untreated, 25 men treated, 25 men non-treated. You got it? So that's stratification for small numbers. And if I have a reason to stratify, if you don't have a reason to stratify, don't do it. It's extra work. But if you do, do it. So read about it. I think stratification is pretty clear. Run should occur as late as possible. I remember I mentioned that before. Don't do it before participants decide to be in. Placebo is a biological inert substance we talked about. I'll skip that. I want to get to the real deal here. Measurement issues. Reason for collecting baseline information. That is key. I've seen a published paper, they didn't have baseline. Clinical trial. Bad journal, isn't it? Very bad. Because that's the minimum. That's a minimum. A baseline assessment going to tell if your randomization works. Because in your baseline, before the intervention starts, before your treatment start kicking in, you get what people really are, and you tell to the reader one day when you publish this thing, if the age groups are equally distributed between the two groups, at a minimum, if the gender are distributed, if some factors that you know because you're a scientist, you're reading paper, are associated with the treatment on the outcome, if they are equally distributed between, you know, treated and untreated group. And that's what the baseline gives you. That's the minimum. But it also helps you to assess, you know, eligibility, subgroups that may respond differently. You are the scientist. You're not talking about just the baseline for paper to put in a paper for a clinical trial, but you also have information to look into subgroups that may respond different to treatment. Okay, so you're anticipating effect modification. So you need to do a baseline assessment of all people in the sample that you included for random treatment and non-treatment. Factors to consider while collecting outcome data. Participants, study participant, clinicians should be blinded. I mentioned this to you earlier, mentioned over and over again. You should blind them. They should not know. They're collecting data, but they don't know, to reduce the likelihood of information bias. Blinding can be evaluated in the study by asking participants for their best guess about which treatment they received. And we did that. Okay, it's very important, because if the absolute majority don't know what they received, you're guaranteed that here and there might be one that knows. But they may not know. They might just guess right. But guessing right 50% of the time is impossible. Usually you see a preponderance of, I don't know. Okay, so that's a very simple way to see if your blinding works. It's not inherent to trials, but should be used whenever possible, as placebo effects are powerful. So you should blind them. Okay, blinding requires placebo or use of alternative treatment that cannot be distinguished from treatment. So you only, and you should only do blinding and placebo together. Single blinded, the patient doesn't know. Double blinded, patient and the people administering intervention don't know. Triple blinded, everybody is blind. There's only one master, me. the PI, the principal investigator. Factors to consider while collecting outcome data continue. Intermediate endpoint may provide information or reason for success or failure of the study. This is an important concept. Usually you're looking for biomarkers. Okay, we had a trial, an intervention trial, population trial, and what's the name of the? There is a chemical that you can measure on the saliva or the blood or urine. It's urine. Usually urine is cheaper and fast of people who smoke to tell if they're still smoking. It was a trial about creating. I forgot what the name. What's the name of the substance? It's cotinine. Yes, cotinine measurement. Thank you so much. So that's a good endpoint for a trial in which you're trying to see if people quit smoking, really. So it's a group of quitters versus no quitters. But then you do a cotinine like we did in Missouri, and 50% of quitters had cotinine very high. I mean, they're not quitters. They're smoking at least once or twice, hiding. Their wife didn't know. Nobody knew it. Okay. Yes, true. Okay, let's all go there. Once you say that's important information about cotinine and tobacco that in my states, in the US, United States, Missouri, pot, I mean, marijuana, maconha, it's legal. So you can always smoke pot. Unbelievable. Most conservative state in US, but it's not. It's legal for treatment, supposed to be treatment. They allow what we call haven cities, like Columbia. My city is a haven city. You can smoke, you're not going to be arrested. So that's kind of free. But it's for most of the state, it's legal marijuana for treatment. But man, I met 2 or 3 people who are treated for tobacco. So what's your disease? I'm really disturbed mentally. Okay, let's go back to work. The relative risk estimate the true benefit of patients receiving treatment relative to those who are taking placebo. Why I'm bringing this? Because I'm going to talk a little bit. It's not analysis yet. We're going to talk about analysis at the end of this lecture. But because I'm talking about relative risk now, is because I'm going to use the term. So just to remind you, here is not the observational design. Here's intervention trial, a clinical randomized design. You have risk for the group that are treated versus the risk of the group who are taking placebo or usual or traditional treatment. So effect size estimation, a very important concept in statistics, but especially true for clinical trials. If the outcome is dichotomy, means yes or no. Bernoulli, folks, binomial, right? There are 2 common ways to estimate the effect size. Percent reduction in the absolute risk of the outcome or percent reduction in the relative risk of the outcome. Both are very acceptable. And when I send this lecture to you, I forgot to edit here. I'm going to put about, there are 3 websites I know, but at least one of them I'll give it to you, that you can go there and say, hey, I want to reduce relative risk from X to X, or the absolute difference, the risk difference, and from X to X, it will give you the power calculation for you immediately. You just feed the parameters. There are tons of places like that. Okay, so let's go look into percent reduction, the absolute risk, which is the most common way of doing. If mortality is 80%, 8% mortality in the placebo arm, and 6% in the interventional arm, then the percent reduction mortality is, come on. You see how that's calculated? Is very simple. Now, you don't know that up beforehand, but you need to use that to calculate your power, to calculate your sample size. So you review the literature on the issue. Or if you have no literature whatsoever, you had, remember you had your ideally in a randomized clinical trial in a phase 3, right? You don't your phase 2, right? Your phase 2 is the mini pilots. Don't need to have power, but it's already showing the difference. So from that trial, you should have some number. You should have published that. If you don't, you'll be in trouble to be funded for your trial or to get your paper published. Or if you're lucky, somebody else did a trial, not as good as yours. That's why you got funded to do a different trial, which is testing the same hypothesis, but in a different way, the better way. Then you have their numbers to use here. But that's how you go after those numbers, okay? Because, hey, that's the whole purpose. I'm doing a trial to prove that I'm changing. I already know the change. You with me? Trying to understand what I'm saying here? So you need to have some guessing, good guess, or ideally from the phase 2 trial, you have some numbers you can plug in here, or somebody else studies. So if you want to experience a reduction, actually the absolute reduction here is 2%, right? 8 to 6, but 2% compared to the original percent that I had in reduction, it's 25% further reduction. That would be the right word here, 25% further reduction. Both are reduction. One is mortality is 8%, go to 6%, you know. Percent reduction, the relative risk, that's a little different, but, you know, not commonly used. If in the placebo arm, an exposure carries a relative risk of 3, intervention arm, a relative risk of 2, we calculate percent reduction in this way. Very similar, see that? Very similar calculation. A 33% reduction in the relative risk. Okay? You can go quickly, but because you can read that later on. But it's better to do this. Okay? And there's a lot of name for it. Cook's distance. There's a lot of stuff. For if the outcome is continuous, we usually speak of change in standard deviation units. And when we do meta-analysis tomorrow, I'll show an example. Okay, one study we've done, and I can show it to you. What do you mean by that? Standardized. For example, a special program raised children's IQ from 100 to 105. It's only a tiny amount of change, right? 100 to 105, but IQ is hard to change. We know the standard deviation of IQ in the population is 15 points. Then you can standardize. Standardize in simple statistics just means divide everything by the standard deviation, by a measure of the variance. Okay, so you have your change and you divide by the standard deviation. You have 1/3 of a standard deviation improvement. And this is a very powerful way to do it because remember it's standardized normal distribution, the Z distribution. You may be, I'm 1 standard deviation to the right, 1 standard deviation to the left. So you can say that your treatment changed 1/3 of a standard deviation, the effect. That's a very powerful and clinical, clear way, undistinguishable from anything else. This is more useful than saying a 5-point improvement. And it tells you how large the 5-point change is relative to the variation. You see how important this is? Because if I have a huge change, listen to this. Let's say instead of 105, I happen to be 120. Let's say I have 120 change in IQ from 100 to 120. That's a 20% improvement in IQ. But if that came from a study in which the variation was very large, when I do a statistical test, I got nothing because I have incredible random variation. But if I estimate that in terms of standard deviation, and I say to you, there was an improvement 1/3, or in this case of 120, you'll be like 20 over 15, you'll be like 100%, you'll be like 1.1, okay? That's powerful because it took care of the random variation. So implicit, when you do elaborate your expected effect size in terms of standard deviation, you're taking care of the issue of random variability, okay? Because the random variability is going to affect your power of the study. It's going to affect your test statistics. So you know you got nothing. So say, hey, I got a 5-point increase in IQ. Say, how many standard deviations is that? I can say I have a 20-point increase in IQ. Huge. So how much in terms of standard deviation? It's only 1.1 or, 2 point, what? Actually, sorry, 1/3 or 1/4. Okay, 1.1 is good. It's be like 110%. Okay, but anyhow, so the random variation is in there. So you should use for continuous values always a standardized measure of the effect. Okay, to estimate. Let's go more a little bit about intention to treat. Outcomes analyzed by intention to treat or by origin assignment to treatment groups. That's what the intention to treat is. If people are changed over time from treatment to treatment and vice versa, You should not analyze them like they are at the end of the study. You should analyze them as they were at the beginning of the study. Okay? This meta-analysis maintains the integrity of the randomization because that's the purpose of the randomization. So if you violate that by allowing people, and technically sometimes we have to, you allow people to move, but you don't analyze them as such. That's all I'm asking you. Intention to treat to say, I will not violate the randomization. Otherwise, it's not a randomized clinical trial. It's a pragmatic trial. It's a non-randomized trial. I cannot call, and confounding may be very strong. Selection bias may be very strong in this treatment if I allow them, and I analyze them as such. So if people migrate from non-treatment to treatment because they learned the placebo didn't work too well, the blinding didn't work too well, and people heard about it, it's an important treatment, it's a rare disease, and as a killer disease, people may migrate. You ethically cannot avoid that, but you don't analyze them as such. You analyze like they're in the original group, and that's going to bias towards a no hypothesis of no association, if and only if the treatment is effective. We're going to be dealing with that with type 1 and type 2 error later on. But you with me on that? Why you do intention to treat? Because that was the purpose of randomization. And I'm trying to avoid selection bias through randomization and confounding bias. If I'm trying to avoid those and allow people to move and then analyze as they were at the end of the clinical trial, they're already in the different group that they already started. Okay? So then I'm biasing my study on purpose. So I don't do that. Intention to treat just to guarantee that my original estimation or expectation for type 1 and type 2 errors too, it's there. I'm not violating that. Okay? The outcomes can be analyzed by actual treatment that the study participant received as an adjunct to intention to treat. So yes, you can analyze them like they are at the end of the thing, but you also do the intention to treat analysis. You do both. Okay? Why you do both? Because that's your reality. You should do both. Always do intention to treat, and if you like, you do also analyze them with whatever they end up. So you have two analyses. If they are both the same, you don't lose anything. If they are very different, you stick to the intention to treat analysis. However, this method introduced a possibility of confounding bias that affect all observation and study. I mentioned that already. So analyzing the clinical trial with people who have migrated from treatment to non-treatment and vice versa, non-treatment to treatment, violates everything I wanted to do with randomization. It includes adding bias when there is none. You are adding bias. You don't know where this is going, especially confounding bias, but allow some kind of selection. The effect of new treatment may vary in relation to characteristics of the study participant. Modification is present. Comparison between treatment groups can be made safely within subgroups. Okay, if defined before randomization. So you need to make sure this is a priori analysis. That's what he meant here. You don't want to analyze your data after you see what's happened. No, you can't do that. You need to have your whole design, including your analytical steps, all delineated before you collect your data, before your people are assembled to treatment on treatment. That's called a priori analytical steps. That avoids this. And then you can then analyze within subgroups. You can do reanalysis of the data within subgroups. You're not doing multiple testing. That's another problem you want to avoid, multiple testing in a clinical trial, because then you are violating type 1 error. We're going to see that later on. It is such a, doing an intervention trial, it tests you everything in statistics and epidemiology. But the analysis is the simplest of all, because you have randomization. If you're doing a continuous outcome, it's just a t-test, nothing else. Okay? It's X that you found minus the average of the X divided by standard deviation of the difference between the two, which is a poor estimate of the variance. That's your t-test. That's it. That's logic.
That's something interesting, because most epidemiologists are used to observational studies, and they have to adjust for other variables.
Yeah, good point, Solange. Good point. Solange,
that's not the case in normalized.
You're right. Yeah.
You don't have to.
Yeah, exactly what I say. So I have a statistician here confirming that I'm saying is correct. In a randomized clinical trial, if done right, you don't need to do anything else. Or complex modeling design. I'm going to do a multivariate logistic regression in two-stage and this, because no, there's no, you randomize. And you have your simple table 1 on the randomized design, shows the characteristics of the populations called treated population and untreated. If the all proportions are identical, why would you do analysis with complex? You're actually violating another principle of statistical testing. You're underpowering your study. The more, we got that at some point, the more parameters you're trying to estimate in a regression, the less power you have. It's a matter of mathematics. There's nothing you can do about it. Every term, and if you are lucky and you have a lot of variables that have more than one term for the variable, you create dummy variables. Let's say I want all the races to be included in my dummy. So I have, like in America, 13 race and ethnicity. Now with gender, I have, hey, male, theirs, mare, yes, his, he, she, what. Then you end up with like tons of variables in your regression. You underpowering your study. All you need is a simple t-test, dummy. Yeah.
You cannot adjust for everything.
Yeah, absolutely. Good point, Solange. Excellent point. So point is, if you have a well-done, randomized clinical trial, double-blind, control, you don't need complex analysis. You just need a simple test. It will be a chi-square or a t-test or a z-test if you have a large number. Okay? Remember, t, z, chi, they're all related. Chi-square is nothing more than a z-square. Okay? However, comparison between treatment groups can be hard if subgroups are defined while analyzing the data. You don't do that. You do it a priori. You prepare. The way I do it, folks, I'll give it to you. I create all the tables, the analytical tables ahead of time. I call mock tables. Always. I prepare. I say we're going to do A, B, and C, and then I create a table for that. Table 1 is going to look like that. Table 2 for this and that is going to look like that. That's the relative risk. This is the estimation of effect by risk difference. This is the standardized difference. I want to see it. You know, I put everything and then put X, 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 just to occupy the space, and I have the tables ready. So it's a priori. So you don't do analysis of subgroups after you see the data. You do a priori. You plan that. So let's move on because there's much to talk about. What time is it? You need to do a break now. I'll go another 15 minutes, folks. Bear with me. It's very important. Concept of power. Type 1 error, false positive. This question?
No question.
Okay. Type 1 error, false positive, occurs if an investigator rejects the null hypothesis. That is actually true. Remember, the null hypothesis is setting you up. You're going to do statistical tests. You need to have a null hypothesis and alternative hypothesis. I know all of you studied that. That's why I did not review that. I can't. And the limited time we have, I cannot go back to the basic of statistics. But you have, you know, a no, HO, it's called H sub O, usually. And alternative H sub A, okay? Which is to say, hey, my null hypothesis that diabetic and non-diabetic patient will have the same A1C at the end of this trial. That's a null hypothesis, whatever's the treatment you're giving them, okay? So the alternative hypothesis, A1C will be better for the treatment group than non-treatment group. You can write in many different ways, okay? So, but type 1 error is a very powerful stuff. If you violate principle of type 1 error by doing intention to treat and all the things, don't do that. But type 1 error basically say, hey, I reject the null hypothesis when it's actually the null hypothesis true. So what do we do to prevent that? We set this limit at a very, very stringent level, okay? And that's your alpha level. We will talk about that later, maybe not. Maybe I will. In the example I have exactly that. Type 2 error, false negative. If the investigator rejects the no, there's actually false, okay? Fails to reject the no, there's actually false. That means you have no power in your study, you're under power. And you do that if you do multivariate regression in a perfectly randomized trial. You're wasting power. You're creating unnecessary underpower analysis, okay? But also, you don't have enough people. You miscalculate your power, your sample size calculation. We're going to go over that quickly. So I brought this for you because I like, this is like a jury. So you are like a You're the lawyer. On the left-hand side is the judge decision. Right-hand side is me, the technician, Roberto, Solange, the statistician. So, judge decision, innocent. The defendant did not commit the crime. On the right-hand side, no hypothesis, no association between Tamiflu and psychotic manifestation. This is a study that people say, okay, you take Tamiflu, you go crazy. Is that true? So let's do a study. The study was done, and this is the possible scenario of the outcome of the study. It was a clinical trial, okay? Clinical trial in Tamiflu and psychotic manifestation. So I don't want to tell you what the result was, because it was a little bit of psychotic. I don't want people to be afraid of taking Tamiflu, because if you're very old and you have a bad influenza, you better take that because you may die. It's like a bad COVID, okay? So, but anyhow, it shows that there is a little bit of psycho going on with Tamiflu for some people. But let's say the possibilities before the jury make the decision. So the defendant say did not commit the crime, innocent. The statisticians say there's no association between Tamiflu and psychotic manifestation. That means Tamiflu does not cause psychotic manifestation. Tamiflu did not cause it. Here say this guy did not kill. Got it? Guilt. Defendant commit the crime. On the right-hand side, there is an association between Tamiflu and psychosis. On the left-hand side, rejecting, standard for rejecting innocence beyond a reasonable doubt. On this side here, levels of statistical significance. That's my type 1 error, alpha. Okay? Correct judgment, convict the criminal. Correct inference, conclude that there is an association when one does actually exist in the population. I will never know that, but that's what here happened. And the jury never knows that too. So statistics is very similar to a jury. Think about the analogy. Correct judgment, acquit an innocent person. The person is really innocent, and I say, no, you're innocent. The jurors decide rightly. On the right-hand side, conclude there's no association between Tamiflu and psychosis when one does not actually exist. That's a good result, actually. Those two results I just described as an excellent result. Now, the one here is funny. Convict an innocent person. Okay? Incorrect type 1 error mistake. That's what you're doing. Conclude that there is an association when there's actually none. And that's why the probability of making that mistake, we make it very stringent. We want to make that mistake at the maximum 5 times out of 100 possible trials. If I could repeat that study 100 times, I would like to make that mistake 5 or less times. Okay? You make it stringent. But if you still make the mistake, hey, that's a limit of statistics. And the limit of the jury, you never know what kind of a jury we're going to get. Okay? Incorrect judgment. Acquit a criminal. You're free, man. Man just killed somebody. Here is saying, conclude there's no association when actually there is. Say, no, Tamiflu is not causing it, but Tamiflu is actually causing it. Okay? So that's what it is. I hope you read this. Remember, try to make an analogy. People still make a mistake when they write their papers, their conclusion, your over conclusions. Oh my God, I love it. I say, nah, kick this guy out. The major problem in RCT is small study, making type 2 errors. It's more common than the other one. Because the other one is kind of standardized. Almost everybody accepted. Nobody say, hey, I want to make a 10% alpha. No, they usually write Solange is 0.05. So it's established kind of stuff. So that prevents a lot of type 1 error happening. Okay. What you end up with, though, is underpowering your study. You don't have enough power. Okay. And that brings another important concept to you all. If you're dealing with clinical trials or intervention trials, and your main outcomes improve people's health, with it is. I'm not talking about, I can do an intervention trial in economics or education. It's used for a lot of stuff, the randomization, everything. You can do in other areas. But in health, your main outcome is health. It's improving people's health by eliminating disease or preventing a disease for kicking in, right? If it is, then be aware of statistical versus clinical or population health significance. Because if you improve your power by diminish the probability of making type 2 error, okay, it doesn't mean that this study is perfect. It may be a small effect. If the small effect is not clinically important, but it's highly powerful, statistically, it gives a p-value of 0.005. Powerful statistic, but it means nothing. It's a 1% point in change in A1C. What that good is going to be when measure diabetic patient, that's what I meant, this new drug, is between 8 and 15, their A1C. I want to bring them to 7 or 6, closer to 5.5, which is normal. Below that is normal. Okay? See, that's an important concept. So major problem is power. We talked about it. Example, anticoagulants and myocardial infarction. Let's go over this. I'll give you some numbers here. Sample size for the test, sample size for the comparative groups, underlying proportion of patient would be success, and treatment group, underlying proportion of patient would be successes in control group. That's the little pie, okay? And delta is actually the difference in percentage of success. That's my effect measure. Remember I said 8, 6%, 2%, divide by 8%. That's my effect measure, is my delta. And then you have the alpha level. That's how small you want your type 1 error to be. And your B level is how small you want your type 2 error to be. Okay, that's your beta. 1 minus that's going to give you what you need. Okay, 1 minus beta. Okay, so non-inferiority studies. Oh, I went this. Here's my... Sorry, folks, I got the wrong lecture. I wanted to go over first superiority. Okay, we have to bear with me. We have to go this way. I'm sorry. It's hard to understand superiority if you just go straight to non-inferiority trials. And unfortunately, the example is non-inferiority trial. But just give you some word. In a superiority trial, the traditional hypothesis testing, okay, would seek to reject the null hypothesis of equivalence with adequate power to detect some minimal, clinically meaningful difference in favor of the experimental therapy to satisfy at least as good as and thus demonstrate clinical non-inferiority. Okay, so that's a little different. So superiority and non-inferiority, to confuse people. I'll have maybe later on, next hour, because we are already running out of time, I'll bring a little bit more clear message. I'll work on that for the next 15 minutes. So let's work on this example here. So the power to reject the null hypothesis, okay? So this little wiggle here, I forgot what is omega, right? Is the cumulative, no, not omega, what do you call that? Whatever. Is the cumulative standard normal distribution. So that's your power statistics. And this is how you calculate your sample size based on that, okay? And I tell you what, we're gonna take a break. I'll review that thing on superiority, and then we'll go over this example, because this is very important. I needed to know how to do this, okay? We'll go over this. Okay, let's take a break. I have real numbers here, real clinical trials. And in the next 30 minutes, we're going to go over power and sample size calculation for superiority and non-inferiority trials. Okay? Take some time. Can I work through here?
15 minutes.
15 minutes, folks. Yeah. So, Fred, I need to get to the... It should be here. No. Basically. Vou hide aqui. Já estou na cama, os alunos já estão lá? Só que foi pro fim, não foi pro começo, não. Demora. Okay, so we're back. Let's start where we finished, because this is a whole lecture about randomized trial. Oh my goodness. Can I go straight there? Okay. So we finish over here. Hey, people, please, we stop the lecture. No noise. I'm sorry. So let's Let's regroup again, because now I put the slide in the right order so you can have the concept of superiority and non-inferiority, so that when you look into power and then when you look at statistical tests, which is going to be the next 10 slides, you understand what I'm talking about. So the major problem in RCT is small studies making type 2 error because they don't have enough people in the sample. You all remember from basic statistics, from the calculation of variance. If you think about a continuous variable, how is the variance estimated? And then more important, how the standard deviation is estimated. You remember that n is in the denominator, right? So every time that you have n that is very small, you're going to have very large standard deviation. When n is very big, the standard deviation gets smaller and smaller and smaller. So then you can prove things much easier. Why? Let's think about a statistical testing like a t-test. You know, you have your value that you found, and you have that expected value that you compare to a minus mu, whatever, or an average of something you already know. And you divide that by what? The standard deviation, right? So if the standard deviation is too large, that test statistic is going to be small. So you have no power. But if the standard deviation is very tight, very small, the test statistic becomes pretty big, and then your p-value becomes very, very small. Because you can then easily beat the null hypothesis of no association. You follow that rationality? So power is very important, but remember again, I can increase power incredibly by having more and more people in the study, but it doesn't increase the truth. The truth is, if the effect is small clinically or from a population standpoint, it doesn't matter how much power you have. That's another consideration you have to have. I'm talking about statistical power, not the power of the new treatment or intervention to actually improve your health. Okay? So then you have these factors here. When you want to calculate the power of a study and, more important, the sample size, these are the factors you need to look at. Alpha level is the level that you determine to make a type 1 error. You want to make it very small. B usually set around 20%, okay? Because you want to make sure that you have 80% power. 1 minus 0.20 is 80% power or more if you have more. But there's a trade-off. The more increased power, the more it affects the other side. So you have to be careful. Usually the standard, they'll have a statistician in the group here, it's usually 80% or 0.20. And then for alpha is 0.05 or less, not more. I've seen studies 0.10 published, okay? So let's go about superiority and non-inferiority trials. A superiority trial investigates whether a new treatment is better than the active control or placebo by a specific margin. That's very simple to understand. That's what you all thinking. So if I could determine the null hypothesis could be something like mu of the new, mu meaning the mean, for instance. Let's say you do mean hemoglobin, or better, mean A1C, okay, which is glycated hemoglobin in your blood that indicates if you have diabetes or not. You know, 5.6 is a cutoff. Below 5.6, above that, you begin to be in the diabetes territory. 7, you're frankly diabetes. And a person who's decompensated or not compensated diabetes, way above that number, okay? So you say mu for the new treatment minus the mu for the placebo, the control group, it's equal to something. In this case, it's less than or equal to the expected margin of change that you expect to see, okay? Say if A1C, I want a 0.2 reduction, actual 0.2 or 0.5 reduction, or a 1 on A1C, okay? Reduction, 1.0 reduction. That's what you want. That's your typical superiority trial. Investigate whether the new thing is better than active. That's how you think, right? Until I started this thing about 10 years ago, 15 years ago, and the first time I heard that, no, it's longer than that, maybe 20 years ago. It's like I always thought there's only one hypothesis to test, but there's this non-inferiority thing, which is the other stuff. In practice, many people took the superiority, just saying, hey, the mu, the mean of this group minus the mean of the control group is 0. Okay? If it is 0, then that's my null hypothesis, means no effect. The treatment didn't improve anything. A1C is going to be the same for those, or the difference between them is 0. On the other hand, if it's different than 0, I say there's an effect. That's a a two-side alternative. Okay, so you can do that. With A1C, it would be hard to justify, but you want to see if there's any difference. That's a superiority. A non-inferiority trial, I have to read this because it's not intuitive. You basically say, okay, to demonstrate and try that new experimental therapy is at least as good as the standard therapy, a statistical test or interval of confidence interval must rule out clinical inferiority with high probability. Must rule out clinical inferiority with high probability. Demonstrate a clinical trial of a new drug is at least as good as the standard therapy. You must rule out clinical inferiority with high probability. That means you cannot be in the territory or be even equal to delta. It has to be different. The term at least as good implies equivalent, but not necessarily superior efficacy. It's statistically impossible to demonstrate equivalence, prove the null hypothesis of no difference. You cannot prove. You can just accept or reject it because of the weight of the evidence. And this author, Blackwater, proposed a one-sided significance test to reject the null hypothesis that a standard therapy is better than experimental therapy by a clinically accepted amount. So that's how non-inferiority trials are set up. A one-sided test, okay? One-sided test that the standard therapy, to reject the null hypothesis that standard therapy is better than experimental therapy. You're rejecting the hypothesis that the experimental is better. You see that? So don't get too confused. Read carefully, because it takes a whole lecture on that. And the mathematics to create this formula for non-inferiority, it's mind-boggling. Even though it's very similar to the other one, there are some details about it. I just wanted to show you so you know there are two things called superiority and non-inferiority trials. What mostly people present is superiority trials, so there's no concern. But sometimes you need to go after that non-inferiority trial. For equal sample size and effect size is difference in proportion. Investing the power expression gives one simple formula. I think is a simple formula for non-inferiority trials. Hypothesis: in study where the plan is to perform a test to hypothesis compare the mean of a continuous variable in a single population to a no mean. So you have your universe and you have your sample. Your study is your sample, is the mean you find. And the expected mean is that for no mean from previous studies, from established clinical usage, whatever. Okay, so HO and your no-HO, you basically say alternative hypothesis, the two are different. It's the no mean or historical control. The formula for determining sample size is a little different than the other one. It's just that one. It's that simple because we're dealing with a continuous variable. And in clinical trials, many times, more often than not, we're not dealing with relative risk. We're dealing with absolute difference between the parameters we want to estimate in a continuous universe. Interval variable, continuous variable. You all remember that, right? Like body weight, hemoglobin levels, A1C, chemicals in your blood. It's all continuous variable. So your formula is very, very simple. Look at that. It's a beauty. You have the effect size at the denominator. That's your estimated effect of impact. Okay. So alpha is selected as Z of 1 minus alpha over 2. Okay, which is based on 95%. And the value of the standard distribution holding 1 minus alpha of 2. That's the cumulative distribution on the Z that gets to that point. That's 95%. For example, if alpha is 0.05, then 1 minus alpha and a half is 0.975. So you want 1975 of the distribution to be included in that Z value of 196. And 1 minus beta is the selected power. So it's a very simple formula. So for 80% power, okay, your Z is going to be 0.84. For 90%, it's 1.282. Okay, so just read this. It's very simple. I'm going to show examples now. And the examples are going to be from that study. Let's read it. So all the examples are coming from that study. Investigative hypothesized that people free of diabetes, fasting blood glucose, a risk factor for heart disease, is higher in those who drink at least 2 cups of coffee a day. So the hypothesis that people drink at least 2 cups of coffee a day, okay, have a higher level of this fasting blood glucose. Section studies plan to assess mean fasting glucose, okay, after 2 cups of coffee. The mean fasting blood glucose in people free of diabetes, 95 milligrams per deciliter, with standard deviation of 9.8. So we have values here. If the mean blood glucose level in people drink 2 cups a day is 100, this would be important clinically. So that's what I consider to be clinically important. So I set up my effect expectation based on what's clinically important, 100 milligrams, okay? How many patients should be enrolled in the study to ensure that the power of the test is 80% to detect this difference? So that's a very fair question. I read the paper and I reformulate as a study for you. So if you read this carefully, say, how do I calculate the power? It is here. Okay, remember the formula I just told you before? Okay, so your effect size is going to be 100 minus 95 divided by 9.8, which is the standard deviation from previous studies were established. So you got 0.51 of the effect size. The effect size represents a meaningful difference, okay? We now substitute the effect size and the appropriate z-values for the selected alpha and power to compute the sample size. We just plug in 196, 0.84, you got your effect size denominator, you got your square. So you need 30 people. That's your sample size for this study, okay? However, I'm giving you a little trick here. If you say, you know, I can enroll these people, I know my population, the way I'm going to do this setup, and I think I'm going to lose 10% of them. It's very simple. You got your 31 people that you need for a sample size, divide by 0.9, because that's, you can only get 90% of real people you can get. That gives you 35. So now you can lose 10%, you still get your 31 people that you need to have enough power. You follow that? Is that a easy mathematics? Not complicated. The effect size is basically saying how much change I'm going to get relative to the standard deviation. That's all I'm doing. It's a standardized effect. Remember, I told you for continuous variable, it's always important to look and to standardize in terms of standard deviation. That's what I'm doing here. I already had the value standard deviation. I expected 100 to be an effect size I want to measure. If less than that, I don't care. If I don't have power to detect from 95 to 97, I don't care because it's clinically not important. I want my power to detect a difference of 100 or above. So I say, okay, 100. That's the effect size I want. And whatever value I have from the past was 95 for the average for this thing. So I want to detect a 0.5, a 5 difference in the fasting blood glucose. A 5, I'd say, what's the value? It's microgram per deciliter, right? I forgot. Where did I put that? Yeah, milligram per deciliter. So I want to detect a 5 milligram per deciliter change. So there we go. You got your performance population. You got your calculation, everything. I also give you a sample size for one sample dichotomy. Sometimes you're not. Most often than not, you may not be interested in that. It's very simple. Look at the effect size. P, remember the proportion? That's a binomial, folks. That's a binomial, right? So you got your P here, P1 minus P0. P0 is the expected, is the ideal value you want to get. Okay? I'm sorry, the value that your reference value. So you got your PQ of a, and when in this case, it's just the P is like a Bernoulli, so it's PQ. Okay? So you have your effect size, you have your formula, you plug the effect size with the values that you have from previous, you plug 0.84 and 1.96, boom, you go. So number to treat, this is a very useful measure to understand and the total value for the intervention. A trial reduced the outcome from 10 to 5%, 50% reduction. What is the end needed to treat? Okay, numbers needed to treat, 90% were in effect because they didn't get the outcome in either group. 95% were unaffected because they did get the outcome in both groups. 5% had a different outcome, or 1 in 20. You need to treat 20 people to get one outcome you would not have had in a control arm. Okay, so you have your people there, you can do that. And there are formulas to do that for you. Okay, I'm not going to get into that. It's a very simple number there in mathematics, because I wanted to cover a lot of material. We have 1 hour and a half of another lecture. I want to finish this one and start the other one, and then finish that on the third term. Okay? So let's go back again to superiority and non-inferiority trials, because I'm going to get you real numbers here. Remember that I showed that before to you, how you set up this, your statistical hypothesis. There's something about the properties and the statistical test theory, and this guy's less suffering. When comparing two means using an unpaired t-test, a significant result is equivalent to a two-sided 95% confidence interval for the difference in means, not including delta of 0. On the other hand, a non-significant result is equivalent to 95% confidence. That's what I mean by superiority trial. Read it. Remember that for two-side superiority trial, the no and alternative hypothesis is delta equals 0 and alternative hypothesis will be delta different than 0, respectively. It is used to compare statistics aspect of superiority equivalence and non-inferiority by making use of non-property or statistical theory. And that's what he's doing here. I want you to be aware of that. Numbers to show how we do this statistical testing from superiority perspective. Streptokinase heparin treatment versus RTPA, which is pretty much in use now. That was the original study in 1993. What is RTPA in Portuguese? You remember? Okay, what you remember? RTPA, what is it in Portuguese? Okay, well, it's a treat. We call it RTPA in English. Anyhow, so you have trial here. How many people in intervention? See the size of these groups? 10,370 in one intervention arm. The other one is 10,348. Okay, this is published. That's the publication. So you end up with some people who are dead after myocardial death after 30 days of a myocardial infarction. Okay, so that's you want to see if one group is better than the other. RTPA plus heparin is better or worse than streptokinase plus heparin. So hypothesis test is set up as such. You can review that back, but it's exactly from 10 slides before. It's the same thing, just now it's in terms of not mu, average, or mean, so continuous variable. We're talking about relative risk, but it's the same ideas. You are showing how to do effect size for relative risk and for attributable risk before. Just go back if you're in doubt, but it's basically the same thing. We're not going to spend much time, but what that's important to see is that in that study, it resulted in a p-value of 0.0028 and a two-sided confidence interval that includes, the delta. So the test for non-inferiority was done. No, I missed another file because I did both tests. I don't know where I put it. Forget it. The bottom line is you can have situation where your test for superiority is going to give it confidence interval that include the null hypothesis, but the test is not.
Is tissue plasmina gene activated.
Okay, tissue plasmina gene activated. No, I want in Portuguese.
Ativador progênico tissular.
Ativador
Plasminogênio
tissular. Activador plasminogênico tissular. It's a straight translation. So is that how they call it commercially here? Because TPA became the commercial name. It's actually the technical name, but just for people to know. Yeah, forget it. Don't worry about it. Don't waste your time. I want you to just read it. Ask me a question about this. We're not going to spend too much more time on this. I give you power calculation, this statistical testing, review it, ask me a question. I'm going to give you a final example with proportions so you can see it. This is a risk of vent circuit change for VAP. Okay. At randomization, this is table 1, folks. Remember the table 1? Table 1 is the one that you show how people are different than the other group. So you have the 7-day change, no routine change, and you have your p-values for change over time. This is published by Kolev, Annals of Internal Medicine, previous intubation, age, male, white, premorbid lifestyle score, Apache score, that means how severe the patient hospitalized with these conditions. At randomization, previous intubation, previous intubation. You can see that both groups are very similar for any of these characteristics would affect the outcome of interest. What is VAP?
The left icon, surgical diagnostic.
Yeah, it's a little different, but it's still not, it's not significant difference, 0.07. Okay, it will not affect statistical calculation too much. They're all no significant change. And that's what you get when you randomize people. Okay, you get similar groups. Okay, risk of vent circuit, this is the continuation. Okay, and then witness aspiration, tracheostomy, and fiber optic bronchoscopy. Receive antacid, receive aerosol. You got a little bit of a difference here in the tracheostomy. Tracheostomy is actually a very different of the two groups. It's also because of what we're trying to show, I believe. I'm trying to remember what trial was that. A long time. At any rate, you have your numbers here of a trial. Your interventions don't change in 7-day change. Okay. So you change the circuit of vent and the surgical theater, and you're looking for, I forgot what a VAP is. God, I plugged for one public patient or not, and I can't remember. But the intervention is just a change in the vent circuit of a surgical theater when you're operating people, okay? And VAP, I think it's infection. I want to bet, but I'm not sure. So you have your relative risks, the crude relative risks, the adjusted relative risks, and because there's so many people, and why they adjusted, remember the discussion we had before? On the two groups, the randomization is very good. Something happened, the randomization is very good, but not perfect. Look at this one here, tracheostomy. The treatment group has 52, 34%. The other one is 19%, highly significant. And one group here, surgical diagnostic category, is not significant, but it's nearly significant. So it might affect, so doing just a simple analysis with a chi-square, you may not be wise. You also want to do some kind of regression here. At any rate, that's why you see adjusted. I don't even know if they did that. I have to read the paper again. They may have done just a stratify analysis, stratify and tracheostomy, and stratify on the group diagnostic category. The two variables, there are a difference between the two groups. You can do a stratify Mantel-Haenszel chi-square analysis, which takes the difference in the group, the proportion becomes the inverse of the weights that you use to come up with the same odds ratio or the same chi-square test for difference in relative risk. Okay. So you end up with this situation. We have the crude relative risk is 0.85. The adjusted relative risk is 0.68. The confidence interval includes the null hypothesis and relative risk. You all know the null hypothesis is equal to 1, meaning the risk in the group in the numerator, which is the treated group, divided by the risk in the denominator, the non-treated group, is the same. If they are the same, arithmetically, the value is 1. So if I cannot exclude the null hypothesis of 1 for RR equal 1, then, I have no effect. Here you have nosocomial pneumonia. Okay, that was it. And that number is too small. Okay. Here you've done the analysis now by person years. So instead of binomial now, I'm looking at person years. See that? I turn all these people, 147, 153, and say how many person years they contributed. And how many, does it matter, the analysis? I give more or less the same thing, a little different. The crude is 0.95, used to be here, 0.85 is 0.94. And the confidence interval is 0.66. It still does include the null hypothesis of no association. Okay, a non-inferiority statistical testing would be something like that. I'm gonna go quickly here, see what the value is. We project to know if the one-sided alpha level is greater than this value, and what is this value that I set up? Is 0.10. So the test statistic gave me a confidence, a p-value, a t of 0.10. Change of 0.10, 0.10 is greater. No, actually, how much is it? It's going to be 0.0572, which is less than 0.10. Thus, we cannot reject the null hypothesis. So the statistical tests agree with the simple confidence interval and the relative risk for non-inferiority trial. So review this carefully. This is yours. I just wanted to show to you there is something else called factorial design on the same randomized clinical trial. Luiz and I tried 2 factorial designs with NIH, didn't get funded, but would have been beautiful if they had been funded. So in a factorial design, you get your random assignment exposed to treatment A, exposed to treatment B, and then you have some people exposed to both treatment A and B, and unexposed to treatment A and B. That's a factorial design. You combine all possibilities here, okay? Can be more if you have, 3, 4, 5 arms, you can end up factorial design with 4 groups. So the question, Marianne Stevenson. My project is a clinical trial study. With the intervention group, we are having 3 meetings to talk about healthy eating and horticulture therapy. It is a project with a primary care patient from 3 UBS in São Paulo. Some of the participants were only able to attend 1 or 2 activities. Is it possible to calculate the difference between going to 1 activity, 2 activity, or 3 activity? And I would like to know if he has any suggestions for this situation so we do not lose the data of those who did not attend the 3 activities. Yeah, absolutely. So your intervention is actually, being trained through the activities. So if the person has 3 activities that has the complete training, 2 activities has incomplete training, 1 activity has very incomplete training, and no activities has no training. So you do have an intervention with 4 levels. No training, little training, some training, and complete training. And you can create a gradient. For instance, if you're lucky and you have an effect, and then the people have no training whatsoever, no participation in the activity, they have the worst outcome. That proves your point to some extent. If and only if the other groups start going up, the outcome is getting better, especially if there's a gradient. The people in the middle, 1 and 2, have some improvement, but the people who have the 3 activities have the major improvement. So you prove your point, you have a gradient. You can combine 1 and 2 sometimes. When you break too many groups, you lose power, but you can combine group 1 and 2, it doesn't matter. You're really looking for is the contrast between those who have 3 activities versus those who have none. That's your main test statistics. That's how you set up your analysis. But you have a gradient. Okay, when you have a gradient, let's say 3 level, you say 0, no activity. You have 1 to 2 activities another group, and 3 activities the third group. So you have 3 levels, and then you find a gradient. You can analyze the contrasting the last level versus 0, and then the second level versus 0. Okay, to get 2 measure of association, 2 measure of the difference. If it's continuous variable, you can do the same, but you have 3 levels, not 2. You have 3 levels, 3 means to compare. And more importantly, you can analyze them separately, but you can also analyze as a t-test. Let's say you have a relative risk. Group 3 versus group 0, relative risk of 2. Group 2, which is 1 and 2 activities combined, versus 0, relative risk of 1.5. Okay, so you show the gradient because the relative risk for a reference called 1 is relative risk of 1. So you have 1, 1.5, and 2 for your comparison. You also can do a test in which you do a test statistic of the trend. You do a trend test. You can throw that on a linear regression. I know it's not linear, it's a categorical, but you can throw, and the test statistic of that is actually testing the linearity of those responses. Okay, there are many ways to analyze this. So yes, you can. Okay, factorial design, you remember how you do it? You just distinguish the possibility. It's a arranjo in mathematics. You were asking a question? No. The other, so that's a factorial design. Or the intervention design, I mentioned the factorial treatment. That's how you set up your factorial design. Treatment A, treatment B. Some people have both, right? Some people have none. That's your factorial design, that right there. Okay. The other one is crossover design. People have treatment A and then they also exposed to treatment B. And there are very specific situations you want to do that. Read about it. Strength, we already mentioned. I'm going to skip this. Read it. I put some 2 key references on that non-inferiority and superiority. Read this article. It does explain very well, like Kishore. Okay. And then the power and sample size determination, you can find even more formula in this website from Boston University. You can see the author, Lisa Sullivan. She is amazing explaining things simply, okay? And I stole her material and I threw it here, but I made a reference to her. Okay, so I need to go to another lecture. Help me out.
This one randomize it or
non-randomized?
Non-randomized. Click here. Just up here, yes.
What time are we supposed to finish?
At dawn.
12:30? So let's go to the other one then. So we still have time. So we still have a full hour and a half, right? Yeah. Okay. Let's go to the other one. No.
This one.
No, this will be the last one. I thought I only have half an hour. Is the clinical trial. That is analysis.
This?
Yeah. Is it sharing? You stop sharing?
Yeah, just change it. This
is one of these randomized.
Randomize it.
It's randomized clinical analysis. Okay, I think this is it. Yeah, this is it. Well, your friend.
Let's see if it's the one they are watching there.
Yeah. Can you check? Is it Alessandra? Can you check? Please, Alessandra? Can you check?
Okay.
It's okay. Oh, okay. Michelle's there. I forgot. Thanks. Okay, folks, we're going to continue a little bit the randomized trial very quickly, just to give it a flavor of more analysis. There's something called completely randomized pair match stratify. We talk about stratify. I forgot to mention pair matching. I did the permutation, the block permutation. Yes, I did. Design depending on unit of randomization. I want to emphasize this point very clearly to you. The randomized clinical trials, traditional randomized clinical trials, placebo-controlled, double-blinded, is the ultimate study, especially when you're dealing with drugs, with vaccines, anything like that, patient population. But when you're dealing with large population, communities, large number of people, major interventions that change systems, change settings, you want to do a group randomized clinical trial, okay? In which the unit of sampling is no longer the individual. The individual is still the interest. I'm going to analyze at the individual level, but I'm sampling at the group level. You follow that? In a randomized clinical trial, traditional or most intervention trials, I randomize, I sample and analyze at the unit level, meaning every person, every patient is my unit of sampling and my unit of analysis. But in situation like I just described, in which the group is an interest because the intervention is everywhere. There's no variance in intervention. There's no change in intervention across individuals in the same group. What change is the intervention across groups. And you expect that. For instance, if you design a new strategy in healthcare setting, I do teach a lot more than just traditional epidemiology. I teach a lot of managers in healthcare because my department and I were interested. Way back 40 years ago, I was a mini hospital administrator, and I took a whole year in training in health administration. Okay, so I deal a lot with healthcare systems, and sometimes the intervention that's going to help the patient life, it's a strategy in the whole health system. If you don't start the strategy everywhere, you start in one of the hospitals, your system. So you see if that thing work, but that creates natural condition for comparison. You better then take advantage and set up a clinical trial, get money from NIH, and allow me to do the right thing, which is randomize into treatment and non-treatment groups. You with me? Follow that? So when you have a situation like that, that's an extreme example. I want to randomize at the group level, but that creates a little problem. Not a big problem. It can be dealt with. The little problem is when you randomize at group level, but you analyze it at individual level, individual within each group, okay? what you have in the traditional statistics, you sample people randomly or things randomly, and you estimate the variance. What is the variance? The variance is a function of real difference across individuals. Let's say you're measuring height. Well, not everybody's the same height. I used to be 171 centimeters at age 18. I know I'm probably 169 by now. Okay? So my brother is only a year older, and that man is 188 centimeters. How is that fair to me? But that's the way it is. Okay? So that variance is between individuals, but there's also variance because people change over time. There's variance because of measurement error. All variance is measuring all of that at the individual level. Okay? But if I'm talking about system, if I'm sampling hospitals, you know, and I'm intervening at the hospital level, everybody in the hospitals have the same intervention. There's no change. Patients receive the same intervention, all of them equally, no matter what, because it's a system-wide change, okay? But across hospital, the interventions vary because hospital, even the same intervention, they may implement them differently. So there is variance. Now I have a situation in which the individual, I'm analyzing the data of a patient in this randomized, group randomized trial. Then the variance from this person no longer is going to come from the change across individuals, and the measurement error across individuals also between the system. I have two levels of variance. So my variance is going to be two terms, the group level variance and the individual level variance. And that's a larger variance. So group randomized trial have much less power than the individual randomized trial. Because of that, the variance is large. And variance is large, your denominator of your test statistics, all of them, the n and the variance goes down, right? At the bottom, you're going to have trouble with that. So I just wanted to watch about cluster randomized design. The trial profile analysis always by ITT or protocol, I would say, which is intention to treat. Always set up baseline characteristic. Crude effect of treatment needs to be calculated before you do any adjustment. And most often it is not needed if it's a very good randomized clinical trial and it's not a group randomized trial. Effective treatment just for possible confounded. It's possible, like I showed the example a few minutes ago, in which tracheostomy was very different in the two groups, supposed to be identical, but for some reason it wasn't. And diagnostic, I think, was something about group diagnostic was also different. It was a variable of importance. Therefore, the final analysis showed not only the crude, but the adjusted measure, and they are a little different. Okay. Effect modifiers, you need to pay attention to that. That's not confounding. Effect modifier concept, very simple. We all know about drug interaction, right? You take a pill to sleep, and then you forget and you drink half a bottle of wine, and then you're dead. That's interaction between, you know, benzodiazepinic and alcohol. You all know that. One potentializes the effect of the other. So in epidemiology, effect modifier acts the same way. You combine the two, it gives effect greater than the units individual, but not necessarily the sum of the two or the multiplication of the two. It could be either. It depends on whether this interaction is multiplicative or additive. Okay. So, and that I'm not going to get into that type of analysis. There's also something in analysis called secondary sensitivity and subgroup analysis. Sensitivity analysis, not well done. Many people don't do it. I'll always do it unless the trial is perfect. But if you lose people, lose to follow up, like you do in a follow-up study, cohort study, or your clinical trial lost people to follow up, or people migrate from group to not. You do intention to treat analysis, but you also can do a sensitivity analysis when you do the no intention to treat analysis, because you need to do both. Okay, what is a sensitivity analysis? What if these people who came from here to here, instead of doing that, they all have stayed this way, and on the other hand, the people in this group, this many people come here. Stop playing with the number. When you lost the follow-up, you say, okay, I lost 100 people in a trial with 1,000. What if all these 100 people all treated? All these 100 people have such and such confounding. That's sensitivity analysis. You start throwing darts and dirt in your analysis to see if it falsifies what you had before. Okay? So in that way, you are strong. You say, oh, this model works. Doesn't matter how I treat this thing, it's always robust. It gives the same result. That's sensitivity analysis. The protocol analysis, always. And intention to treat analysis, always. I don't accept any variation of that if I'm doing a true randomized clinical trial. If I'm doing a pragmatic trial, that's another story. If I'm doing a non-randomized quasi-experiment, that's a natural experiment. If we have a chance, I'm going to show you a very interesting study done here in Brazil, financed by the Minister of Health of Brazil with World Bank money directly. I designed that study. It was done 15 years ago in a whole state. It was an intervention trial, but it's not randomized, but it's as good as, I don't know if I have a chance to show you, but it's very interesting. Non-eligibility, non-compliance, had all the UNES, reason to exclude. These are good reasons to exclude people. Did not attend all visits. Example of our colleague who asked the question, should exclude them? Depends. If it's critical and you only have 2 levels, but you can create 3 levels, don't exclude them. Include them and say, hey, they don't come. Actually, you want them. And therefore, it doesn't match what you actually had in your question. But that's the real issues about the attendance to visit. Move out, drop out. There nothing can do about that. You can read about the adventure of ITT. Intention to treat is not possible, can be relaxed. In phase 1 and phase 2 clinical trial, which explore property of treatment in idealized conditions trial. So you don't need to do that, and it's not the purpose. You only do intention to treat in phase 3. That's efficacy measured to after. That's the golden standard here. Conduct the flow chart, provide numbers of subjects. Whenever you do your studies, do this flow chart. How many are registered? Remember that tree I showed? Every one of those studies from case control to knowledge shows a tree. You actually write that tree down with numbers when you write your papers for publication. And also it tells you how much confidence you have that you don't lose people, okay? Register for eligible, randomize, assign to each group, because you may randomize and then during the assignment, something happened in the implementation. The clinics who are supposed to assign right didn't do it right. You need to make sure all of that is done right. By group, you need to show all those ends, the end, how many people are getting what at what time and what progression. So that's how you do your flow diagram. So you can plug your numbers here. You can use this. Create one for yourself and plug your numbers, okay? Now we're going to talk. These are examples. I wish I would know how many slides I have here. Yeah, 43 slides. That's a lot. So this is a study called CREATE. I'm using this for a few example analysis. There's a glucose, insulin, potassium infusion, okay, postulated to improve mortality in patients with acute S10 segment elevation. That's STEMI, in English called STEMI. It's really, people have coronary heart disease, likely. 99% of them do. There might be some other disease that makes you prone to have an infarction, okay? So your ST, that's the wave from S to T wave on your electrocardiogram, it's elevated. That's a very high risk. I don't want to be there, okay? Anyhow, so this drug, glucose, insulin, potassium infusion, okay, very low cost, is supposed to improve mortality in patients with this elevation. They're prone, but they're already about to have a heart attack, or they're get angina, they have pain or something. So the randomized control trial was actually a group randomized trial. I wanted to show you that because it's very important, cluster type of randomized trial. 470 centers worldwide, 20,000 patients more or less, with STEMI who presented within 12 hours of symptom onset. Mortality outcome was mortality. Cardiac arrest as a non-outcome, or cardiogenic shock, and reinfarction at 30 days after randomization, okay? So all these are endpoints of my study. So therefore, it's almost like I have 1, 2, 3, 4 trials here. Because for every endpoint, you can have slightly different set of predictors anyway. 20,000, 21 patients, that's how they came down, remember? I told you how to break down your tree. Initiated with 10,110 on one group and 10,091 in the other group. They lost some people, not too many. It's pretty good, unbelievable. Okay, trial analysis by ITT or per protocol, right? Baseline characteristics, we're going to look into that first. Let's look at baseline characteristics. You want these things on the left and right to be identical, not perfectly exactly, but so how this study is going is pretty good. Look at that. Is there any number that not nearly identical to the other side? Everyone is. Look at everyone. Unbelievable. Some numbers are actually exactly the same. Okay, so the randomization really works, even though it's a group level randomization, Solange. Okay, not at the individual level. Remember, these are 10,000 people in each group, a clinic level. The randomization on a clinic level. But, whoa, look at this. Classification and randomization 1, 2, and 4. These are level of severity or how likely to die from that cardiogenic effect. Look at the last number, 106 to 157. Whoa, 1.6, 1.6 exactly. 13.2, 14.2, 85.1, 84.2 is unbelievable, perfect. Crude effect of treatment. Here's your crude effect of treatment. Estimate the magnitude of the effect of the outcome measure. P-value can also be provided. The outcome measure can be of 3 types: binary, death or not death, or multiple level improvement, marked, some, none. Continuous blood cholesterol could also be measured. Survival type, time to death. That's survival. Remember? The case fatality and survival. The statistical method using now depend on the type of outcome you want. And here, you can see the death and the usual care versus the infusion group. It's very close, 9.7, 10. So the relative risk is only about 1, which is mean no effect. And not surprised, you have a p-value 0.45. Non-fatal cardiac arrest was very similar to in the two groups. No effect, p-value 0. But you could see that from the relative risk. It's always good to present both. In statistics, we tend to put too much power and credence on the p-value, but the most important information for anything in health is the confidence interval. Just tell me more or less what I'm seeing. Okay, the size of the effect estimation, which is relative risk or risk difference, and the confidence that I have around that. For instance, I have more confidence when the confidence is about tight, and they're decently tight here, and and they all include the null hypothesis. So I have to believe it, and the p-value is matching that. Sometimes the two are not exactly right there. The p-value is showing an effect, and the confidence interval is barely. Just barely included. I don't like that. And the effect is small. But here, there's no effect on death, no fatal cardiac arrest, cardiogenic shock, or infection for the treatment called GIK infusion relative to usual care. Okay? And there was a group randomized trial. Remind you that this analysis was done, I should have put a warmer here, is that this calculation included random effects analysis of the cluster effect on the variance. I don't get into that, but the reason for that, here we have a binomial, okay? But you have 2 levels of variance in a binomial. That's your risk, your relative risk estimation. If the risk in the exposed group is a binomial, the risk in the unexposed group is a binomial, the relative risk will be a binomial. But I have 2 levels of variance, so I have 2 levels of variance of the relative risk. Okay, and therefore, to take into that into account, I have to do a complex analysis, regression analysis for cluster randomized design that incorporate the weights and the correlation. It calculates the interclass correlation coefficient across individuals and across group, so that we can incorporate that in the calculation of variance. It's a multiplier, becomes a weight on the variance, so the variance is blown up. So maybe there's a, if you have done an individual level trial, you would find a little bit of a small effect. But in a group randomized trial, it did. But also the confidence interval will not be full by the power of the study, because the relative risk is what it is. It would have been the same one with a cluster randomized design or the individual level randomized design. The relative risks are very small, and they're all hovering around 1. So there's no real effect. I have no doubt about that. Okay? So effective treatment adjusted for possible confounding. So when I look at the crude analysis, there's nothing there, but I did adjust for the variance at the bottom. Here, I don't only adjust for the variance, but I adjust for all the other possible confounding effects going, and I do a model here. But you saw these things are very similar across group. I should not be worried about evaluating confounding, but because of the variance estimation is so complex. When I do through regression, it does a better job. The algorithm for finding variances at two-level hierarchical models, like in SAS, would be like Prof mix. Okay, so you would do a better job in estimating the true variance underlying that. I'll skip some things and I want to show you that produce adjusted measures associated between treatment and outcome is adjusted for the effect of any possible confound, but in this case also does a job of representing the variance of the relative risks estimated a little bit better. I didn't show the numbers. And you also want to stratify sometimes, and this is an example that you want to stratify because there's some variable that need to be stratified. There's none here, so there's no stratification. Secondary sensitivity analysis, they've done some in this study. Analysis, they are of secondary importance. They've done some secondary analysis, meaning the main purpose of the study is to test if GSK infusion will improve death, cardiogenic shock, and blah, blah, blah. But they all did other secondary analysis. They look into the effect of GIK infusion on phlebitis and hyperglycemia. What do you think, Solange, about doing secondary statistical testing, not the a priori organized, the main purpose of clinical trials, GSK and cardiovascular death? Here, I'm doing something completely different. Don't you think this is like multiple testing?
It might be. Sometimes the researcher plans a study, and his main outcome is actually a secondary endpoint.
Well, but you should have thought.
Yes. So first, the try to have first a primary endpoint, but I think they are valid.
They're valid. I'm not saying that. Okay, so the discussion here is that should we do that one? Second one is that what does it mean? For me, it means the following. If you have that as your main hypothesis to test, you already did a priori. That's okay. It's one like it had like actually 4 hypotheses to test. It was death, a cardiogenic shock, and 2 other things related to the heart. It just could have added phlebitis and hyperglycemia. I know for a fact it wasn't the case. That was a secondary thought. Like later on, they say, oh, maybe we can do something here. I see some difference here. It's a posteriori, okay? And you actually inflating type 1 error. If I had the time and do a statistical test, I'll show it to you a simulation I do that prove if I think about it afterwards, I can find significant stuff. It doesn't mean they actually exist because I'm creating them. So because of that, they should have done a multiple testing adjustment. They should have divided the p-value by the number of extra testing they're doing. So if they've done 4 + 2 is 6 tests, that's a p-value divided by 6. Instead of 0.05, you have 0.05 divided by 6. It's point what? 0.015, something like that. Okay? So it'd be very, very small to accept that, you know. But again, they found p-value, significant p-value 0.001, so it would have found anyway. Okay, but that's a secondary test. That's not the main purpose. I just wanted to show as an example. And they went about doing other subgroup analysis, but that one was planned. The subgroup analysis were planned. Okay, and then you have discussion. You strengthen your weakness. I'm going like if I'm going to a paper in this extended part of the clinical trial, randomized clinical trial study. And I use the example of a cluster randomized design to show you that it is possible, is there, and there are many now. About 30% of the randomized clinical trials are cluster randomized design now, especially in the healthcare field, that you have an entire change in therapy for whole groups of patients. So you don't randomize a small group, you do effectiveness trials. So a cluster randomized design for clinical trials is the best trial for measuring effectiveness because you're dealing with large population, dealing with complete implementation across many people, okay? Describe the protocol deviation from the study's plan, percentage, show your percentage, present statistics. So this is just a little bit of an extra presentation to guide you how to go about presenting. And what I was talking about before, a cluster randomized trial, I'm giving you in 3 or 4 slides here. And this paper by Donner is very important. I could list here also a chapter of a book that I wrote in statistics that shows that for intervention trial, but I'll be too self-serving. I'm showing Donner, who is the magician of this area. He created this area, Donner and Clark. They have the ultimate paper and they have a book on it. So random assign take place at organization level, cluster analysis at the individual level. We talked about it, okay? So, and that's why I say there's also this design effect. This is very important because it affects your variance estimation, okay? So design effects say how much variance I should add to this modification in the design. Does the design modify my variance estimation? It does. You create levels of variance at the group level, individual level. They have to be add up. But I can estimate that there's something called, goodness. I forgot. I should have written here. Maybe it's there. A procedure in SAS that does calculation for you. But all we're talking about is this. Once you have a cluster randomized design, you're going to have this DE design effect, which is 1 plus this row here that multiplies M minus 1, where M is the average number of subject sample per cluster. If you talk about those patients, remember, there are 200 some hospitals that are involved, 10,000 patients. So the average is actually 10,000 divided by 200. Okay? You have been about 500 people in each group. So that's your M. So M minus 1, 500 minus 1 is 499. And this row here is the interclass correlation, intercluster correlation coefficient for the correlation across cluster. It's a pro-core in SAS with a slash, I forgot what we call it. So you're basically going to find what the interclass correlation is. You multiply that by that number and add value 1. So if your design effect is more than 1, mean you cannot just assume the normal variance you have. You have to actually adjust your variance to the interclass correlation coefficient. So when you do a cluster randomized design, usually the variance is multiplied by a factor of 2. That's the design effect. These values become 2, depend on the M, how many people per cluster do you have, okay? So this is just for you to see that. I want you to see that. Do another one, unit of randomization clinic, 463 women recruited by clinic on average. And you have the ANC model. You have abortion, that's your interest, antenatal care trial. There's a paper, I put the paper reference, you can look it up. You end up with that many single births in each group, okay? The new ANC model clinic is a full strategy. It's called new ANC model. And the standard ANC model clinic is the standard clinic, a treatment for pregnant women. And the numbers and this trial is there. So what you're looking for was the principal provider, specialist, obstetrician, general practitioner, midwife. You want them to be similar across groups, and they are, right? Because you're dealing with the antenatal care treatment, a new model of antenatal care versus a standardized model, which is the traditional, and your outcome of interest is birth, or death during birth, or stillbirth, or low birth weight. I forgot what exactly was the outcome. Compare the standard model of antenatal care with new model emphasize known to be effective improving maternal or neonatal outcomes as fewer clinic. Didn't say exactly, but I'll review it. I think it might be just healthy birth. Okay, antenatal care clinics. Here's the results that you have. Okay, here are some of the outcomes. Yes, low birth weight is one of the outcomes. The other one's preeclampsia, eclampsia, postnatal, postpartum anemia, and treated urinary tract infection. Okay, so these are some of the outcomes. This is the results of the clinic. You see there's no effect. I like to show no effect because it's so common, people showing a lot of effects. This is the true stuff, no effect. Okay, and they actually estimated odd ratio. They're probably using logistic regression. I forgot to look it up. Anyhow, these are some of the stuff I wanted to show you quickly on analysis. It's all yours. This and the original make up the randomized trials. Okay, now we're going to go into the territory quickly of non-randomized design. What time is it, people? 11:30. You want to take a quick break of 10 minutes? So we go to non-randomized designs, and I will show you one quick example. There'll be a lecture, of maybe 20 minutes, and then I'll show for 20 minutes a presentation to illustrate a non-randomized design, okay? So 10 minutes, folks, we'll be back. Of those decision tree for experiments and non-experiment, okay? You have randomized control trial, cluster randomized trial. I'll show both of them already to you. Stepped wedge design, adaptive design, hybrid design. Adaptive design and hybrid design are such a complex view, macro view of all these studies. It's just saying we need to build them in an adaptive or hybrid design. And the hybrid is because I want to evaluate not only efficacy and effectiveness, but also sustainability, maintenance, permanence of the intervention after all the efforts to create the intervention is all gone. Is it stable? Is it sustainable? That's adaptive hybrid design. We're not going to even deal with that here. But there'll be another course in epidemiology that I'd love for you to have it. So the wedge design and a variation of that is the one I'm going to show to you very deeply is the rollout design, which are good for community trials, okay? Can also be used as a quasi-experiment, but there's other much simpler quasi-experiment or non or natural experiment types of design. The before and after control, before and after type of study, interrupted time series, regression discontinuity, and difference in difference. I'm going to show an example of what we call difference in difference. And they're all within the natural experimental design realm, okay? So here within the traditional trials, I'll show you the RCT, the cluster RCT. I'm going to show you quickly the stepwise design, and the rollout being an adaptation of that for ease of implementation. Here I'm listing them again, what we went through. These are all possible designs, trying to read about them. So stepwise design is a sequential rollout of an intervention or implementation strategy to individuals or cluster, individuals within cluster or clusters over multiple periods of time. Require the order of rollout to be random. It basically, I'm saying, I'm going to do a community trial in a whole state. I'm going to show an example of stepwise design I did here, hopefully for 10 minutes in Brazil. It was funded by the World Bank and the Minister of Health of Brazil. CNPq had money on it. I don't know how much money, but anyway. So you basically roll out your intervention little by little, not all at once, because it's not feasible. Or the government or an institution is already planning on doing a rollout and over time. So instead of just doing over time their own design, you say, hold on a second, can we do that randomly? If you do that randomly, you liberate the intervention little by little, city after city, but not, I want sit A, sit B second. No, can you do it randomly, sir? Governor, can I do that randomly? That's what you do. So that's a rollout design that is a step wedge design. There are characteristics of it, so we're going to go over that. All individuals in a cluster will receive the intervention at some point. This is usually useful when a program, when intervention is being rolling out the intervention across the whole region. So everybody's going to get it no matter what. I'm just, hey, give me a chance to design in such a way that it approximates a real randomized clinical trial. If you randomize the timing of the intervention and the release of that intervention. If you follow that, if the group here is lost, the group over there will be lost too. So, example, in the state of Pernambuco, we evaluated a program called Academia das Cidades, okay? And the evaluation was good, but it was not perfect. It was observational design, okay? It was actually, the initial study was a prevalence case control. Okay, so it has a lot of possibility of bias, selection bias, confounding, a lot of issues. But it showed the program has a tremendous effect if it happened to be true. Now the state of Pernambuco is saying, hey, we like this program in the city of Recife, it's 25 years old program, so good, we're going to spread to the whole state. I say, sir, can I ask you a question? How long will it take you? About 2 to 3 years to get to every city in the state. That's the estimation. I knew when the government said 2 to 3 years, 5 years. Okay, so I said, good. I said, can I help you design how you roll out this intervention? I say, yeah, welcome. Come. I say, okay, let's roll out randomly. Okay, across the communities. Everybody's going to get it. Okay, but while some communities are getting the first year, some I'm going to get only at the 5th year, 5 years later. Therefore, the Community had the intervention 1 year, in the first year. At the end of the 5-year period, they will be compared, their outcomes will be compared to the one they had on the last year. You follow that? The one they had last year had no time to have an effect. So they are like natural control group. You understand how this thing works? For 4.5 years, they had nothing. So they're perfect control. You understand how this rollout goes? So that's a stepwise design. And it's all about rolling out the program in such a way, in sequential way, that create natural comparison group. It's very similar to some of the randomized trials I mentioned to you before, in which everybody gets it, but in a different way. Person gets the intervention A, the other group gets intervention B, but then later on I give intervention A for those who have intervention B, and I give intervention B to those who have intervention A. But that's a patient randomized clinical trial. That's kind of a variation of the factorial. It's called crossover design. Here, there's no crossing over. I can't not do that to random allocation in steps. I just taken advantage of a rolling out of a program and randomizing the rollout timing of which groups get the intervention. It's like a group randomized trial. The groups getting the intervention are getting them sequentially through a random decision on the timing of the delivery of the intervention. You follow that, folks? Is that too complicated? Can you follow that? Okay. So dynamic wait list and rollout design. Divide the study period into multiple times. That's what we did. Okay. During which subject or groups are randomly assigned to receive the intervention. Balance units into equivalent blocks and then randomly assign blocks of units of time period for adopting the novel intervention. So let's say I have 20 communities and I have 5 years multiplied by 12. That's 60 months, right? So I have 60 by 20. Multiply 60 by 20. How much is that? 1,200, right? 1,200. So I have 1,200 blocks of time in community in groups. And I randomly sample that. Let's say those that end up in the first month are going to get this and this. When I randomly sample that, I end up with random allocation or rolling out of the intervention over time and create natural groups of comparison. You follow that? It's more like a natural experiment that has some control and randomization of the time units. And the first phase, 1/2 of participants are randomly assigned to receive the intervention, the other half to control condition. But I don't know who they are ahead of time. The randomization is going to create that because I'm randomizing a unit of time. Okay? And the second phase, the control condition receives the intervention. So everybody receives the intervention eventually. So it's not unethical because that's a problem with local government. Say, about 30 years ago in Missouri, I tried to do a study like that. And we designed, CDC wanted to pay a senator, learn about it, and say, not in my backyard. Everybody in my community is going to get this intervention. Say, sir, it's a rollout. I don't care about this rollout. The man was very ignorant. They didn't care about that. I want everybody to have it. Forget it. He thought I was doing something unethical, giving an intervention to a community, not giving to another. Because that's what it looks like. Usually, and that's what you actually do in a clinical trial. But if I do a rollout design, everybody gets the intervention. Oh, but it's unfair for those who get later. If you could give them all together at once, fine, I accept that. But if you cannot, the governor of Pernambuco told me it'll take them 3 years. I know it took actually 7 years for every community in Missouri, in Pernambuco to have that. Those are my 2 states, right? Pernambuco and Missouri. You see that how it happens? So it's very ethical, actually. But anyhow. So there you go. You got rollout designs. There's a paper here you can follow. I'll give a few examples of the rollout design. You can read about it. Concept and appeal rollout design. Very committed to wide scale. So policymakers, I actually am getting ahead of myself. I was already described the politicians did that. The politician, the policymaker, the agency, the community, they are very committed to wide scale delivery of a particular intervention. The ultimate desire is to scale out so everybody gets it. Intervention, little no information available on its benefits or potential harm cannot provide to everyone. This is the true situation in real life. They want to roll out an intervention for a whole region, a whole state, a whole province, a whole country, but they have no certainty if that intervention works. Maybe there's a little efficacy trial 300 people to show some effect, but is that true for effectiveness? Will that work? Let's do an intervention evaluation type of rollout, okay? Sub-regions, community can be divided in sub-regional areas where intervention can be implemented independently, outcomes can be assessed in a relatively short period of time. You have to have some conditions. So here's an example of a rollout, okay? Private Brown and Woodford in 2006. Units are randomized when they get the intervention. Units of time, you can see here participant clusters, randomized order, and you here have the time 1, time 2, time 3, time 4, time 5, time 6. Eventually, everybody gets the intervention, but in the first time period, 6 years. The government is going to roll out the intervention 6 years. In the first year, it's just preparation. It's actually happened naturally. It's when you think this is how it happened. The only difference is that they will design who gets first, second, third. Here, I'm doing randomly, which is the same thing. I just have to negotiate and talk to politics to understand how to do a rollout. But you understand, it's all preparation. You naquela lista, se você tem aqui, esquece comunidade A e B. A comunidade A no primeiro ano, comunidade A no segundo ano, comunidade B no terceiro ano. Então você tem os valores dele. Aí você trata todos aqueles que não tem, aqueles períodos, a combinação de período com comunidade, que não tem tratamento, como controle grupo, como todo. E o outro como tratamento grupo. E foi randomizado. O rollout da intervenção foi randomizado no tempo.
Conecta os dados em todos os quadradinhos? Ok.
Sim.
Voltou.
Sim.
Voltou, Eduardo?
Voltou? Não precisou botar no teu computador.
Você quer já fazer a pergunta, responder a pergunta para a Caroline?
Eu quero saber onde é que eles pararam de ver isso.
Dois minutinhos. Um slide mais.
Tem uma pergunta aqui, pessoal. Carolina Krause. Professor, when the study is a cluster RCT in the design protocol. Wow, that's a loaded question. Okay, you have a cluster randomized clinical trial. Okay, so remember, cluster randomized clinical trial is as good as individual randomized clinical trial. And I showed an example, by chance, the baseline assessment of those who have to treat those who have, it's identical. It's better than the previous example was an individual level clinical trial. So it has as many. So there's no bias introduced by randomizing clinical trial as a cluster. There's no bias. The crossover does not introduce bias neither. There's no bias introduced by crossover. Crossover is when you have something that you think people need to have both treatment. You have two treatments that you want to see the effect of both because they're kind of complementary. Maybe there's an effect of treatment A, effect of treatment B, depending, but then there's a possibility biologically that once you have the two treatments, something happened to your body. You already know. I can't remember an example right now, but that's why you do that. Migraine is an example. I'll get to an example later on. I'll send a note to the group. But the point is, these design don't introduce any bias or anything like that. No. Okay? So they don't introduce bias. And changing calculation relative to bias, no. Bias are not addressed by your calculation. Your calculation can address the cluster, can address the random variation that you have in your estimates of the parameters, such as relative risk, risk difference, change, effect size. Okay, they might affect the variance of that. So when you do cluster, you have to adapt to it. But the crossover is not going to affect your random variations. It's not going to affect your variance estimation. The cluster will. Okay, so there's no adjustment for bias during the study. You can adjust the bias to sensitivity analysis. It's not really an adjustment to bias. It's a how much the bias, if I'm thinking about selection bias, a loss to follow-up, or information bias, or placebo did not work, okay, or something like that, then I can say sensitivity analysis. Say, what if these people all have been this way, not that way? What if these people who I lost, all of them in treatment who are male or female or something? That's a sensitivity analysis. You can understand if bias is affect your group. Usually the rule of thumb is when the people that you don't have information on is very small relative to the total sample size, there's no bias. By the way, can you see my image? Because there's some message coming on the other computer screen here. Alessandra, can you see my image?
Yes.
Yeah.
Okay, and the slide. Okay, so I hope I had answered your question, Carolina. The second question for Carolina is the only difference in the crossover in a step wedge is that in the step wedge, the group receiving the intervention does not return to the control condition. To some extent, but remember, most often, I would say 90% of the time, you want to use crossover in individual level clinical trials, randomized clinical trials of patients. Whereas the wedge design is usually used for interventions at the community level or clinic level, because it is a matter of feasibility or acceptability or political correctness. And so wedge design or rollout designs are used to address the issue of politics and ethicality, perception that being too scientific and being inhuman and being unethical. No, it's ethical because you're actually doing a rollout, sir. You do exactly, but not scientific. I cannot measure. I cannot say for certain that randomization took place. But if I randomize, I get the same effect that you have. Okay, so let's go over this randomized through a rollout. So look at the example of the rollout here. I have time periods from 1 to 6. Let's say this is a 6-year rollout because I learned that the intervention is going to be rolled out in this community by community. Let's say I have a region with 100 cities, okay? And I have 6 years to roll out this intervention because that's what I learned, the plan. It's planned by government. They're going to roll out, okay? In reality, if I let them go, just do your business, government, they will come up with something like that. What you see this drawing here. First year, nothing happened because they're planning, they're organized, they receive the verbas, the resources, the money, right? And they're planning, the planning phase. Second year, they enroll over the first time period, a bunch of cities in this first group here. So 1 to 5 is the group of cities, okay? So I have 100 cities and 6 by 5, 30 groups. I have about 33.3, about 4 cities in each group, more or less. Okay. So in the first year, nothing is done. Then the second year, 4 cities are enrolled. So you see the first time combination of time and grouping or cluster of cities is enrolled. And then there's 2 of those clusters. There'll be 8 cities enrolled, and there'll be 12 cities on the year 4, and there'll be 16 cities in year 5, and there'll be all cities, whatever is the rollout and the number of cities you have. Maybe my numbers are not right. You got the picture. So that's what the rollout naturally goes. All the difference I'm doing, say, government, let me do the rollout using a random assignment instead of you or your officer in the field deciding which city gets first, or which mayor has the biggest voice. Because they may say, hey, I want my city first. okay? And they may get first, but in my way, I randomly assign. Everybody's going to get the same way. But if I randomly assign, then the rules of randomization works, and I end up with groups that are comparable, treatment and control groups. And who are my control group? My control groups, folks, is any of the cities that on the first year had nothing, because all of them are control of themselves. Think about it. On the first year 1 here, which is the first column, everybody didn't get anything. So in the experience of that group relative to the endpoint of interest and relative to all the other confounding, that means nobody got any intervention the first year. Second year, only a few had the intervention. So I'm comparing everybody against itself and against some other. So the person, let's say the city on the last block here on the year 6, time period 6, the last block that got dark by a purple shade, okay? That last block has 5 cities there. Those 5 cities only received the intervention the very last year. So they always be a control group because there's no time for them to have effect of intervention. So bottom line is I end up with a lot of city control and treatment group, okay? Because the experience, by the way, I'm measuring endpoints and everything every year or every month. If it's in a 6 month or 6 year, I'm measuring everything. So you end up with a group of people who are treated. The beauty of the rollout is that by randomization of time, I end up with cities. Let's say I say to me, like in Pernambuco, in my intervention, I knew the size of the city could be associated with the exposure, with the intervention. Meaning the intervention would be better in bigger cities because they have more infrastructure. Because the intervention there is physical activity for the masses. It's called Academia da Cidade. You go to a place, to a suburb, and you change the environment, physical environment in 1 kilometer area, creates a little trail, creates a place where people exercise in group, put a physical activity teacher who's trained in first socorros and urgent care, who's trained in obesity, who can measure things, who knows a little bit of public health and prevention. And they are there free from 6 in the morning until 9 in the morning, and then from 3:30, 4 o'clock in the afternoon until 8:30 in the evening, to help people to exercise in group, capoeira, dance group, whatever. And then in Recife, it's going on for 25 years. And there's over 200,000 people in any given day, any given week, sorry, because there's a combination of possible days in a week doing exercise. We measure that over there. So, and when you have a situation like that, the size of the city matter, the organization of the city structure, the secretariat of the health matter. So all those things matter. We measure all of that. And we measure when they initiate or not. I have an example to show rollout that if I can get in the end, I'll show it to you. But that's what the rollout is, folks. Very important for community trials. Okay, here's some example. Read those papers. Kagalis in AJPH, American Journal of Public Health in 1996. Okay, so standard conditions, single active intervention, standard condition, randomized intervention, AOB. There are many examples of rollout design or wedge designs. How much time I have, because we had that issue. How much time I have?
I think that's 15.
Only 15 minutes. I think they were not 15. Okay, let's keep a few things here. You can read this, send me a question. There's some examples of these studies. I pull it. This one here did a little different rollout of repeated pairs of randomized community. Read it, it's very interesting. There are variation of the themes, but they allow you to get something practical. If you really want to do public health, yes, you can help clinical trials for treatment inside clinic, but you really want these intervention trials, right? It's randomized trials at the level of the community, and rollout is the way to go. And there's variation of the theme. I'm showing a few examples here. Okay, a few examples. You see that? Head-to-head rollout design, Brown. This is a good one. You have an intuitive cohort there, cohort A, cohort B, cohort C. This is a time frame, time 1, time 2, time 3. X and Y means intervention, no intervention. There's the other one that's a variation. That's another paper by Brown. Okay, read those modifications of what I just explained in that first graph to you, the first diagram. Okay, so without limit set of evidence-based community and preventive intervention, this is how I wrote, especially to address disparities across groups defined by race, ethnicity, poverty, location, whatever. We need to emphasize rigorous evaluation of homegrown program. Because what happens at the level of government, a level of big organization, they tend to do too many non-randomized trials because they are the only way. No, rollout is a randomized. I can apply all the rules in randomization. So if I can do a rollout, I better do that. If I can't, then I can do a natural experiment that trying to mimic a rollout. Okay? So rollout designs are appropriate for policymaker community leaders. So it's community trials. Here's some of the papers. Okay. There's a little bit about experiment. I want you to read about natural experiments. But I think you resonate more with you if I show an example. I don't want to be crazy about it, but I think this is going to make the case clearly. If I can get to it very quickly. So can you help me with this, Fred? And here too, I'm going to skip a lot of a slide to go to the key ones, so people understand what a rollout is. This is a real thing. It's not a somebody's paper you need to read a few days from today. I'll show you how we done a rollout. Yes. Okay. It was designed as a randomized rollout, randomized clinical trial design. In practice, it didn't go too well, but the concept is there. Well, it went very well, but not as a randomized. It went as a non-randomized rollout. Okay, it became a natural experiment. But there's some issues around that, the way we designed it, that is pretty good. I don't want to get to that discussion either. Okay, this is a presentation, so it's not a lecture. Okay, but what you had some evidence before through a case control. Remember, I mentioned the level of evidence, cross-sectional, case control. Then you do your cohort, and then you do an intervention trial. We had some evidence this program was working. But then the government, with the very minimum evidence, say, oh, we're going to spend $100 million over the next 5 years to roll out this program. So that's a waste of money if it's not working. And I have every interest in rolling out without evaluating because we're involved in creating the program. So it'd be nice, right? But then I say, that's not fair. Let's evaluate. What if this thing is bullshit? It's just the case control has possibility of huge bias. So that's the way to do it. We design as a rollout. They didn't accept totally. They accept partially. So basically, the program is being expanded to all cities in the state of Pernambuco over a 3-year period. In fact, later on, it took nearly 8 years for them to roll out. When they say 3 years, I told them 5. It took 8 years for them to roll out the whole program. Offer opportunity to augment the evidence about that by doing a rollout design. Okay. We had some prior stuff. So here's the state. Here's the program called PACID. Okay. I'm going to skip a lot of stuff. I use a lot of methods. So basically I say, okay, during the time July 11 to July 14, like, 3 years time, they say they're going to roll the things out. It took 7 years, folks, in practice. Okay. There will be municipalities in different stages of implementation of PACID. And if I roll out that randomly, it will be even better. But even without rollout, you have that naturally. Cities without physical change, re-engineering of available space, or without the profession to offer the leisure time physical activity class, LTPA. I call this X1 or G1, group 1 or X1. X1 is the effect, right? Cities with re-engineer space only. They don't have the physical activity professor. They don't have the classes going on, anything like it. City with the space in the class, professional, and hiring contractor. They're already at advanced level. City with the space, class, professional, training, blah, blah, blah. Everything is working in a combination of those cities. So you have all these possible combinations going on, theoretically. So this is how I designed it. I don't want to get too deep into that, but if you could read those little things, and means non-equivalent groups, because initially it was for equivalent group. It will be just E, okay, or G groups, because it was supposed to be randomized, but they did not allow me to randomize. They thought I was forcing something absurd. It wasn't. It took them 8 years. It would have been a perfect design. It was near perfect because I did not randomize. But bottom line, you end up with N, which is non-equivalent. Equivalent meaning when I randomize, I call equivalent groups, because everything on this should be similar except the treatment. Okay, but here I don't have it. But you still end up with time 1, time 0, time 1, time 2, time 3. You end up with a lot of those combinations. and you can read. I'll copy a little bit of that into the lecture and give it to you, because this is not a lecture, this is a presentation. I'm just skipping stuff. Here's the example of the possible combination of analysis you could do. You see that? So bottom line is natural history of intervention groups, 2 or more baselines, additional follow-up interval, look at either post-test only control group design and pre-test, post-test control group design. So you have all these type of comparison to analyze. And I call this a cohort or cross-sectional with in-time design. Okay, a prior match of stratification could have been on, it was done. There's a lot of stuff. Let me show to you what this thing end up being. Methods. So the outcome variable is actually uptake of physical activity. What's the proportion of the population is actually being physically active before and after those interventions, and between treatment and non-treatment groups, the natural comparison treatment and non-treatment groups, okay? And the conditional interventions were those levels, and I create gradients. Some city had the engineering, a little class, but some have been going on for 5 years. So the other thing I learned about this stuff in prior studies that this type of intervention, once it start working, it attracts more people. It doesn't go down over time. It starts attracting more and more. So once you have an intervention in one place, it kind of takes everybody else. And people who are around the community who have that, they start exercising more, not exactly in the program, but they start exercising. We proved that people who drive by in Recife and see those 5 academies on the beach, it's like 14-kilometer beach in a straight line, they see it and somehow they're more exercise, even though they don't participate in the academy, okay? They become, okay, oh, this is nice, I need to walk on the beach. They start doing it. It's proven. So having the program for many, many years as an added effect of being, okay, stimulating to other people. So you have all these type of gradients and contrast going on. Okay, here's how many variables we measure in these people over time. Baseline in the middle and at the end of the 3rd year. So it's like 3 measurements. You have all of this stuff. Settings, we have the setting, pre and post test. So analysis in pre and post test control group design, an adjusted time multiplied by condition analysis. Read about that. Prior stratification, we stratify ahead of time, fixed effect. Prior stratification with group and strata, random effect, we analyze both ways. Okay. So the truth is, and we use this, I wanted to show it to you. Remember that I mentioned the 2-level variance. There's 2-level variance here because it's a group design. The intervention goes for the whole community, and the cities will have that. People exercise more, even if they don't participate in the program. By the way, we didn't measure physical activity among program participants. That's not it. This is a random sample of the communities. We took random sample surveys of the community before, middle, and after. In all these communities, okay? We took a random sample, randomized. There's, I think it was 500 cities and towns. We randomized, we took a sample of about 75 of those. And within the sample of the cities, we randomized people based on their household, the systematic, random systematic sample of households for every 10th or 14th household to get people in. So we measured their level of leisure time physical activity. So it's like wedge design, rollout design. The only thing we couldn't do is convince them to allow us to do the randomization. But in practice, you end up with that same development of the groups by time, okay? And community. We analyze this using SAS Prox Mix. You can use Stata or SAS to do that. I'll give you a little bit more about that. XT-REG and Stata or Proc Mix in SAS, because our main measure is level of leisure time physical activity. It was a score. So it's a continuous interval variable. Okay, here's some of the finding. 7,185 members potentially active in 160 cities, sample out of the 500. Okay, 14 to 67 members per city, blah, blah, blah. Question, what does the equation look like if city model as a random effect? So we did as a fixed, as a random effect because of those things I mentioned to you. Here's some of the math for those who want to go. I'll throw that at the end so people can see a little bit, you know, and you can copy that. You may be a similar situation in the future and you have it, okay? So I'm going to finish on time. It's exactly, you know, 12:26. my watch. I just wanted to show to you, this is not just theoretical. I've done it. I implemented this in Northeast Brazil with all the difficulty. Actually, this study is amazing because there's some other element I cannot show to you, like geographical software. Okay. Actually, we monitor if people are going to collect the data in the house through satellite. We knew if the surveyor paid by contract firm was getting to the house that was actually sampled. I'm not kidding you. Okay, we are doing that.
Eduardo, another question for you.
Okay. Yeah. Okay, am I still showing this?
People are not watching this.
Oh, they are? Okay.
Thalita.
Khalid asked a question. Does the cultural activity of a group of people interfere that much in epidemiology study and data collection? Does the cultural activity of a group? Again, Khalid, it depends. What you study. If you study an intervention or treatment or an outcome that's influenced by culture, yes, you need to adjust for some measure of culture. But I cannot dream or even see how culture could affect epidemiological study. Well, there is. There is. Let's say you're studying diabetes, a region I know better than even my original state in Pernambuco. Yeah, I was going to say that, exactly. But it was different. It's actually religion and perception of chronic racism. So that culture affects how you look into diabetes in a place called Boot Hill in Missouri. It's a historical rural and more predominantly white, but still a greater number of African-American farmers. We inherit a system of crop farming that is from the slavery time. So they have a perception of diabetes based on their oppression for so many years that affect the study. You need to take that out into consideration and create a variable to measure that. Okay, so it's possible culture will play a role. Sorry for skipping so many things, but you know, here are some of the study stuff we did. You see that? How is you see the geographical software, that satellite image? We went down to the point of the city, street, and household level to see if the surveyor was doing that in that day. It was an innovation in that study. Okay, so it's doable. We can do a wedge design. Please think about wedge rollout design for logical intervention by your city or your state in public health, because we have an opportunity to evaluate better, either as a quasi-experiment, that's what it ended up being, or as a true rollout randomized design, okay, which is a cluster type of design. Okay, thank you all. Acabou? Tá sem.
Conexão caiu.
A gente está conectado, UNIFESP aqui.
Então, a gente está na rede da UNIFESP. A questão é que a internet cai de vez em quando. Apesar de a gente estar na rede.
Agora deu.
You are connected.
So people. Thank you, Thalita. Send more questions to email. I'll leave my email to all of you forever. You can ask me a question. I'll promise to answer within 3 or 4 days because it's a crazy time over there. But I'll promise to answer anything. What? Yeah. But folks, I'm not talking about theoretical things. We've done those things. Look at this. This is Brazil. It was published in American Journal of Public Health. Okay. Thank you, everybody. And until tomorrow, we do with meta-analysis, which basically say, hey, you've done all these studies. They're not too good, but together they're good. That's what meta-analysis is. That's it. I already gave you the class. Hey, relative risk of 1.1, 1.2, confidence interval include the null hypothesis. Hey, I did a meta-analysis, and all these non-significant became extremely significant. That's what meta-analysis is. It's trying to create truth when there's no truth. We'll deal with that tomorrow, okay? I'll see you. Bye, everybody.